500 million years ago, Earth was unrecognizable. No forests blanketed the continents. In fact, no plants or animals lived on land at all. The oceans teemed with bizarre creatures. Five-eyed predators with circular jaws, armored worms covered in spines, and the first ancestors of everything with a backbone. This was the Cambrian period, a time when life exploded in complexity after 3 billion years of relative simplicity. Continents drifted in configurations we'd struggle to map today. Oxygen levels were climbing. Predation had just been invented, forcing prey to evolve armor, speed, and entirely new body plans. Within a geological blink, roughly 25 million years, nearly every major animal group we know today appeared in the fossil record. What triggered this evolutionary frenzy? How did Earth's barren landmasses and alien seas set the stage for all complex life, including us? The answers lie buried in ancient rock formations scattered across every continent. 500 million years ago, Earth's pulse beat to a rhythm almost unimaginable today. The Cambrian period had just reached its midpoint, a geological moment dated with precision to approximately 500 million years before the present. This places us roughly 40 million years after the period's dramatic beginning at 538.8 million years ago, when the planet emerged from the preceding Ediacaran period. What preceded this transformative era? A world locked in the final throes of profound climatic upheaval. The Ediacaran itself had followed the Cryogenian period, an epoch marked by the most extreme glaciations Earth has ever experienced. Between 720 and 635 million years ago, the planet endured at least 2 snowball Earth events. The Sturtian glaciation lasting from roughly 717 to 660 million years ago, and the Marinoan glaciation spanning approximately 650 to 635 million years ago. Each of these frozen episodes persisted for tens of millions of years, with ice sheets advancing from polar regions toward the equator, perhaps even covering tropical latitudes. The evidence for these catastrophic freezes comes from glacial deposits found at paleolatitudes near the equator, revealed through paleomagnetic analysis of ancient rocks. When the Marinoan glaciation finally released its grip around 635 million years ago, Earth's climate system underwent a fundamental reorganization. The mechanisms triggering these snowball events involved runaway ice albedo feedback. As ice sheets expanded, their high reflectivity, between 55 and 80% of incoming sunlight, sent solar energy back into space rather than warming the surface. Ocean water, by contrast, reflects only about 12% of sunlight, making the transition from ice to open water a pivotal climatic threshold. Complicating this ancient climate was the sun itself, which shone approximately 6% fainter during the Cryogenian than it does in the present day. The post-glacial world of the Ediacaran, spanning from 635 to 538.8 million years ago, witnessed the first tentative appearance of complex multicellular life. Strange soft-bodied organisms, Dickinsonia with its quilted body segments, sea pen-like Charnia, and the threefold symmetric Tribrachidium, populated seafloors during what paleontologists call the Avalon Explosion, around 575 million years ago. These creatures represented evolutionary experiments, body plans that would largely vanish by the end of the Ediacaran in an extinction event approximately 539 million years ago. By 500 million years ago, those Ediacaran oddities had been replaced by something fundamentally different: animals with mineralized shells, jointed appendages, complex eyes, and predatory lifestyles. The transition marks one of the sharpest boundaries in the fossil record, a line separating the Precambrian Supereon, nearly 4 billion years of mostly microscopic life, from the Phanerozoic Eon, the age of visible life. What had changed? The physical planet itself had been restructured by ice, volcanism, and the restless drift of continents. The continents themselves occupied positions radically different from their present arrangement. At 500 million years ago, the supercontinent Rodinia, which had dominated Earth's geography for hundreds of millions of years, had completely fragmented. This breakup, which began in the Neoproterozoic and accelerated through the late Ediacaran, scattered landmasses across an ocean-dominated globe. The largest of these new continental assemblies was Gondwana, a massive supercontinent composed of what would eventually become South America, Africa, India, Antarctica, and Australia. Gondwana straddled the southern hemisphere, extending from low northern latitudes nearly to the South Pole. Separated from Gondwana by the widening Iapetus Ocean lay Laurentia, a substantial landmass comprising present-day North America and Greenland. Unlike Gondwana's southern position, Laurentia straddled the equator, placing it in a tropical zone. Further north floated Baltica, the future Western Europe and Scandinavia, and Siberia, each following independent trajectories as the rifting processes that destroyed Rodinia sent them drifting across the globe. These separations opened new ocean basins and created convergent plate boundaries where continental margins collided, generating volcanic arc systems and mountain-building events. The oceans themselves dominated the planet's surface to an extent difficult to appreciate from our modern perspective. The vast Panthalassa Ocean, literally all sea, surrounded the southern hemisphere continents and stretched across much of the globe. Sea levels stood dramatically higher than today, perhaps 100 meters or more above present levels, flooding continental margins and creating extensive shallow water environments that covered what would now be dry land. This marine transgression represented one of the largest and most persistent sea level rises of the entire Phanerozoic eon. The flooding resulted partly from the melting of Neoproterozoic ice sheets, those final remnants of snowball Earth glaciations, and partly from the changing geometry of ocean basins as tectonic plates reorganized. Climate patterns bore little resemblance to modern conditions. Average global temperatures hovered around 22 degrees Celsius, substantially warmer than today's 14-degree average. No polar ice caps crowned either hemisphere. The warmth extended to high latitudes, creating greenhouse conditions that persisted throughout much of the Cambrian. These elevated temperatures far exceeded the cool conditions of the preceding Neoproterozoic era, which had averaged around 12 degrees Celsius during the long intervals between glaciations. What drove this dramatic warming? Several factors converged. Increased volcanic activity along the new mid-ocean ridges formed by Rodinia's breakup, elevated atmospheric carbon dioxide from volcanic outgassing, and the loss of reflective ice cover that had characterized the cryogenian icehouse. The elevated temperatures combined with continental flooding to accelerate chemical weathering of exposed rock. Rain falling on barren, vegetation-free continents dissolved minerals and carried them into the seas, fundamentally altering ocean chemistry. Calcium concentrations surged, providing the raw material for shell-building organisms. Some researchers suggest this calcium influx came from erosion of the Transgondwanan supermountain, a massive orogenic belt preserved today in East Africa, whose roots represent the collision zones created during Gondwana's assembly. Others point to increased erosion during and after the snowball Earth glaciations, which scraped continents down to bedrock and created what geologists call the Great Unconformity. Worldwide gap in the rock record marking the boundary between Precambrian and Cambrian. Strata. The atmosphere itself was undergoing critical transitions. Oxygen levels, though rising, remained below modern concentrations. Estimates place atmospheric oxygen at perhaps 12 to 15% of the atmosphere during the early to middle Cambrian, compared to today's 21%. Yet this represented a dramatic increase from earlier periods. Pulses of oxygenation occurred episodically throughout the Cambrian, driven by complex feedbacks between biological productivity, organic carbon burial, and the formation of iron sulfide minerals in oxygen-depleted deep waters. These oxygen pulses coincided with major radiations of animal life, suggesting that rising oxygen concentrations provided the metabolic fuel necessary for larger body sizes and more active lifestyles. Strangely, the continents themselves remained almost entirely lifeless. No forests, no grasslands, not even simple plants covered the rocky surfaces, the landscape would have appeared utterly alien, expanses of bare rock, gravel plains, sand dunes, and perhaps thin crusts of microbial mats along shorelines where moisture lingered. Without vegetation to stabilize slopes or absorb rainfall, erosion proceeded at rates far exceeding anything in the modern vegetated world. Sediment washed freely into the oceans, creating massive mudslides and turbidity currents that periodically rolled down continental slopes into deeper water. These sediment flows, catastrophic though they were, occasionally created the conditions for exceptional fossil preservation by rapidly burying seafloor communities before decay could destroy soft tissues. The oceans, by contrast, pulsed with activity. At 500 million years ago, the Middle Cambrian, marine ecosystems had already undergone their most radical transformation in Earth's history. The explosive diversification that paleontologists call the Cambrian Explosion had peaked roughly 20 to 30 million years earlier, between 530 and 520 million years ago. During that geologically brief interval, animals evolved complex body plans, mineralized shells, compound eyes, jointed limbs, and predatory behaviors that fundamentally restructured marine food webs. By the time Earth reached the 500 million year mark, trilobites already dominated shallow seas, having made their first appearance around 521 million years ago. These armored arthropods, with their distinctive three-lobed bodies divided into a cephalic shield, segmented thorax, and tail section called a pygidium, had radiated into hundreds of species, occupying diverse ecological niches. The fossil record. Preserving this transformative period comes from extraordinary deposits scattered across ancient ocean margins. The Chengjiang biota in southern China's Yunnan province captures a snapshot of life approximately 518 million years ago, just 18 million years before our 500 million year focal point. This assemblage, discovered in the Yuanshan Formation, preserves over 300 species representing more than 20 phyla, making it the most diverse early Cambrian fossil locality known. The quality of preservation at Chengjiang is extraordinary. Soft tissues, including eyes, guts, gill structures, and even possible brain tissue, survive as mineralized films and compressions, offering paleontologists detailed anatomical information rarely available in the fossil record. These animals inhabited a deltic environment influenced by storm floods, where rapid burial under sediment preserved their bodies before bacterial decay could destroy soft tissues. Similar preservation occurred at Sirius Perset in northern Greenland, roughly contemporaneous with Chengjiang at approximately the same Cambrian Stage 3 age. Though less diverse than Chengjiang, Sirius Perset yields comparable soft-bodied fauna, including early arthropods, preapulid worms, and enigmatic organisms difficult to classify within known groups. The consistency of animals found across these widely separated locations, China and Greenland occupied different continental blocks 518 million years ago, demonstrates that Cambrian radiations were genuinely global phenomena rather than local evolutionary experiments. Perhaps the most famous window into Middle Cambrian life comes from the Burgess Shale in British Columbia, Canada, dated to approximately 505 million years ago. Discovered in 1886 but extensively collected by paleontologist Charles Doolittle Walcott between 1909 and 1924, the Burgess Shale preserves tens of thousands of specimens, representing over 120 species. These fossils accumulated against the face of a high underwater limestone cliff, where catastrophic sediment flows periodically swept down the slope, burying entire communities. The sediments, fine-grained muds that excluded oxygen, prevented decay and allowed the preservation of arthropod appendages, worm bodies, sponge tissues, and even the gut contents of predators. When Whittington and colleagues reanalyzed Burgess Shale specimens in the 1970s, they recognized just how bizarre many Cambrian animals actually were. Marella, the most common organism in the deposit, clearly belonged to the arthropods but fit into no known class. Five-eyed Opabinia, with its vacuum cleaner-like proboscis, seemed utterly alien. The spiny, slug-like Weywaxia defied easy classification. Stephen Jay Gould's 1989 book, Wonderful Life, popularized these discoveries, arguing that the Cambrian explosion represented a period of maximum morphological experimentation, when body plan diversity exceeded what exists today. Though subsequent research has placed many of these weird wonders into existing phyla, Opabinia and Anomalocaris, for instance, are now understood as stem group arthropods. The fundamental point remains. The Cambrian saw the establishment of all major animal body plans that persist in modern oceans. But before these complex fossils appeared, the earliest Cambrian witnessed a more subtle revolution. Small shelly fossils, tiny skeletal elements just millimeters across, appear in rocks dating to the very beginning of the period, around 541 to 530 million years ago. These sclerites, spicules, tubes, and shells represent a highly varied assortment of animals, many of which remain poorly understood and difficult to classify. They mark the first widespread appearance of biomineralization, the ability of organisms to construct hard parts from minerals extracted from seawater. Why did mineralized skeletons appear so suddenly? Multiple factors likely converged. Rising atmospheric oxygen enabling the metabolic costs of shell construction, increasing predation pressure favoring defensive armor, and changes in ocean chemistry providing abundant calcium and other minerals. Equally significant were changes in animal behavior recorded not by body fossils, but by trace fossils, the burrows, tracks, and trails left by moving organisms. During the late Ediacaran, animals produced only simple horizontal traces on the seafloor surface. Starting in the Cambrian, creatures began tunneling vertically through sediments, exhibiting more varied behaviors that provide indirect evidence for mobile animals with differentiated tissues, organs, and directional locomotion. This substrate, revolution as paleontologists call it, fundamentally restructured seafloor ecosystems by mixing sediment layers, introducing oxygen deeper into the substrate, and creating new ecological niches. The very first appearance of the complex trace fossil Trichophycus pedum, the burrow of a mud-dwelling organism capable of sophisticated movement, defines the Precambrian-Cambrian boundary at 541 million years ago. By 500 million years ago, all these innovations were established facts of marine life. The world before complexity, that long Precambrian stretch dominated by microbes and simple soft-bodied organisms, had given way to ecosystems recognizably modern in their ecological structure, even if the specific animals inhabiting them would seem utterly alien to contemporary eyes. The transformation that reshaped Earth's biology did not unfold gradually over hundreds of millions of years. Instead, animal diversity exploded in what geologists now recognize as one of the most rapid evolutionary events in the planet's history. The Cambrian Explosion, as this phenomenon is universally known, ignited approximately 541 million years ago at the very beginning of the Cambrian period and reached its peak intensity between 530 and 520 million years ago. Within this window of roughly 20 to 25 million years, a geological eye blink representing less than half of 1% of Earth's total history, nearly all major animal body plans appeared in the fossil record. Before this explosion, animal life existed but remained relatively simple. The Ediacaran fauna that preceded the Cambrian consisted primarily of soft-bodied organisms with few complex features. No eyes, no shells, no jointed appendages, and apparently no predatory behaviors. These creatures, preserved in rocks spanning from about 575 to 539 million years ago, exhibited body plans that would largely disappear by the Ediacaran-Cambrian boundary. Some paleontologists argue they represented evolutionary dead ends, experiments, in multicellularity that failed to survive into the Cambrian world. Others suggest certain Ediacaran forms may have been ancestral to later animal groups, though the evidence remains contentious. The boundary separating these two worlds is marked by a specific trace fossil, Trichophycus pedum, a complex three-dimensional burrow produced by an animal capable of sophisticated movement through seafloor sediments. This trace fossil defines the Precambrian-Cambrian boundary at precisely 538.8 million years ago, a date refined through radiometric analysis of volcanic ash layers interbedded with fossiliferous rocks. Before this boundary, burrows remained, simple, mostly horizontal scratchings on the sediment surface. After it, animals began excavating vertical shafts, U-shaped tunnels, and branching networks that mixed sediment layers and fundamentally restructured seafloor ecosystems. What triggered this sudden burst of evolutionary innovation? Scientists have proposed multiple hypotheses, and the emerging consensus suggests that several factors converged simultaneously. Rising atmospheric oxygen provided one crucial ingredient. Complex animals with active lifestyles require substantial oxygen to fuel their metabolisms, particularly for powering muscles, processing sensory information through nervous systems, and constructing mineralized shells. Geochemical evidence from sulfur and iron isotopes preserved in Cambrian rocks indicates that oxygen levels, though still below modern concentrations, underwent pulses of increase during the early Cambrian that coincided with major radiations of small shelly fossils and arthropods. These oxygenation events extended habitable zones from shallow coastal waters into deeper marine environments, expanding the geographic range available for evolutionary diversification. Changes in ocean chemistry provided another critical factor. The breakup of the supercontinent Rodinia and the assembly of Gondwana generated extensive mountain-building episodes, creating the Transgondwanan supermountain that stretched across East Africa. Erosion of these mountains, accelerated by the warm, humid Cambrian climate and the absence of vegetation to stabilize slopes, washed vast quantities of dissolved minerals into the oceans. Calcium concentrations surged, providing raw material for the construction of shells, spicules, and other mineralized structures. The elevated erosion rates also delivered phosphorus and other nutrients that fueled biological productivity in coastal waters. Perhaps most significantly, the evolution of predation fundamentally altered the rules of survival. The appearance of animals capable of hunting and consuming other organisms created intense selective pressure, favoring defensive innovations. Soft-bodied creatures became vulnerable targets. Natural selection favored mutations producing mineralized shells, protective spines, the ability to burrow into sediments, or sufficient speed to escape predators. This evolutionary arms race accelerated diversification, driving both predators and prey to evolve increasingly sophisticated anatomies. Eyes evolved to locate prey or detect approaching threats. Jointed appendages developed for rapid locomotion. Segmented body plans allowed flexibility and specialization of different body regions for different functions. The fossil evidence documenting this explosion comes from three main sources: body fossils preserving actual animal remains, trace fossils recording animal behavior, and small shelly fossils representing the earliest mineralized skeletons. Each category tells a different part of the story. Small shelly fossils appear first in the rock record, beginning at the very base of the Cambrian around 541 to 538 million years ago. These tiny skeletal elements, usually just millimeters in length, include tubes, caps, spines, plates, and scales representing diverse animal groups. Many remain difficult to classify because paleontologists possess only isolated skeletal fragments rather than complete organisms. One scheme for organizing early Cambrian diversification, proposed by paleontologist Graham Budd, divides the explosion into 4 successive intervals based on which organisms dominated. First came Tube World, lasting from about 550 to 536 million years ago and spanning the Ediacaran-Cambrian boundary. This interval saw the spread of Claudina and Namacalathus, simple tube-dwelling organisms that constructed calcium carbonate shells. Next came Sclerite World, dominated by animals bearing small skeletal elements called sclerites, the Halkyarides, Tomatides, and Hyoliths, lasting until approximately 525 million years ago. Brachiopod World followed, characterized by the radiation of brachiopods, lamp shell-like animals with 2-valved shells. Finally, Trilobite World began around 521 million years ago, when these iconic arthropods made their first appearance and rapidly diversified. By 521 million years ago, the elevated rates of evolution that characterized the explosion's initial phase had largely ended. This doesn't mean evolutionary innovation ceased. New forms continued appearing throughout the Cambrian, but the explosive pace of diversification slowed to more typical rates. The fundamental architectures were established: bilaterally symmetric, bodies with heads and tails, segmented structures, appendages, sensory organs concentrated in head regions, and mineralized protective coverings. Everything that followed represented variations on these basic themes. The biological innovations that emerged during the Cambrian explosion represent some of the most profound transitions in life's history. Eyes evolved during this period, with compound eyes appearing in trilobites by 521 million years ago, providing the first known instance of complex vision in the animal kingdom. Andrew Parker has proposed that the evolution of eyesight fundamentally changed predator-prey dynamics, forcing animals to develop new defensive strategies when hunters could detect targets from a distance rather than relying solely on touch, vibration, or chemical cues. However, this hypothesis remains controversial, as other senses like smell and pressure detection can actually perceive threats at greater distances in marine environments than vision. Yet their earlier evolution did not trigger comparable diversification. Alongside vision came dramatic increases in cognitive abilities and nervous system complexity. The development of brains during the Cambrian enabled the rapid, coordinated movements required for hunting, escaping predators, and navigating complex environments. Brain-bearing organisms could process sensory information, make decisions, and execute sophisticated behaviors impossible for simpler creatures. This cognitive expansion correlates directly with the novel ecological lifestyles that emerged during the period: active predation, burrowing, swimming in the water column, and filter feeding all required enhanced neural processing. The positive feedback between brain complexity and behavioral range enabled animals to exploit an increasingly diverse array of ecological niches. The major animal groups that appeared during this time constitute nearly all the phyla we recognize today. Echinoderms, the lineage that would eventually produce starfish, sea urchins, and sea cucumbers, made their first appearance. Mollusks emerged, including early forms that would diversify into snails, clams, and eventually cephalopods. Various worm groups proliferated, including priapulid worms that burrowed through sediments. Arthropods underwent their most dramatic radiation, with euarthropods, the group containing insects, crustaceans, spiders, and trilobites, becoming the most diverse and abundant animals in Cambrian seas. Today, arthropods comprise over 80% of all animal species on the planet, making them the most successful body plan ever evolved. Perhaps most significantly for our own lineage, chordates appeared during the Cambrian Explosion. These animals possessed a notochord, a flexible rod running along their backs that would eventually evolve into the vertebral column characteristic of fish, amphibians, reptiles, birds, and mammals. The earliest chordates were small, fish-like creatures that swam in Cambrian oceans, and their fossils from sites like the Chengjiang Biota and Burgess Shale provide crucial evidence for vertebrate origins. The Cambrian Explosion produced the largest and most diverse grouping of animals Earth has ever witnessed. A comprehensive analysis of early fossil euarthropods from every type of fossil preservation, published in the Proceedings of the National Academy of Sciences, demonstrated that when all fossil evidence is considered together, the explosion unfolded, gradually over approximately 40 million years during the early to middle Cambrian, between 540 and 500 million years ago. This finding challenges both the hypothesis of slow, gradual evolution starting 650 to 600 million years ago and the alternative claim of nearly instantaneous appearance at 540 million years ago. Instead, the evidence suggests a middle ground. Euarthropods originated no earlier than 550 million years ago, then diversified over the subsequent 40 million years. Professor Alison Daly, who conducted this research at Oxford University Museum of Natural History, explained that each type of fossil evidence has limitations and incompleteness, but when taken together, they illuminate a coherent picture of euarthropod origins and radiation. The Cambrian Explosion, rather than being a sudden event, unfolded gradually across the lower to middle Cambrian. This timing is crucial for understanding how physical characteristics evolved and which groups developed first, allowing scientists to trace the evolution of features like jointed limbs, compound eyes, and segmented body plans. The uniqueness of the Cambrian biodiversification lies not just in its scope, but in what it represents. Two waves of Metazoan expansion into empty ecological niches. The first wave saw animals exploring niches on the Ediacaran seafloor, while the second expansion in the early Cambrian established them throughout the water column. The rate of diversification during the Cambrian phase remains unparalleled among marine animals, affecting all Metazoan groups for which Cambrian fossils exist. Later radiations, such as the diversification of fish during the Silurian and Devonian periods, involved fewer taxonomic groups and much less morphological variety. Whatever triggered this early Cambrian diversification opened an exceptionally wide range of previously unavailable ecological niches that had never before been occupied. Once these niches filled with successful organisms, limited space remained for similarly wide-ranging diversifications to occur again. Strong competition existed in all niches, and incumbent species usually held advantages over potential invaders. This helps explain why no comparable explosion has occurred since. When empty niches exist, clades can diversify and become disparate, enough to constitute different phyla, but when niches are occupied, lineages continue resembling one another long after they diverge because limited opportunity exists to fundamentally change their body plans and lifestyles. Dating the Cambrian Explosion required scientific breakthroughs in both radiometric techniques and biostratigraphy, the correlation of rock layers based on their fossil content. The Cambrian period itself is divided into 4 series and 10 stages, each defined by the first appearance of specific fossils called Global Standard Stratotype Sections and Points, or GSSPs. The base of the Cambrian is marked by the first appearance of the trace fossil Trichophycus pedum at a reference section in Newfoundland, Canada, dated to 538.8 million years ago through uranium-lead dating of volcanic ash layers. Similar techniques apply to ash beds. Throughout Cambrian strata worldwide have allowed geologists to construct precise timelines showing when different animal groups first appeared. The explosion itself unfolded in recognizable phases, though paleontologists organize these phases differently depending on which fossils they emphasize. Ed Landing's scheme recognizes 3 stages spanning the critical interval. Stage 1, crossing the Ediacaran-Cambrian boundary, saw diversification of biomineralizing animals and the appearance of deep, complex burrows indicating sophisticated burrowing behaviors. Stage 2 witnessed the radiation of mollusks and stem group brachiopods, including hyoliths and tomatids, which apparently arose in intertidal waters where wave action and tidal cycles created challenging but resource-rich environments. Stage 3 brought the Adabanian diversification of trilobites in deeper waters, though relatively little change occurred in the intertidal realm, where earlier radiations had already filled available niches. Trace fossils. The burrows, tracks and trails left by moving animals provide an independent record of behavioral evolution during the explosion. These can be divided into 5 subdivisions that parallel the body fossil record. Flat world, lasting through the late Ediacaran, featured traces restricted to the sediment surface, where organisms crawled or rested, but did not burrow. Proterozoic 3 saw increasing complexity as animals began probing sediments. Pedum world initiated at the base of the Cambrian with the appearance of Trichophycus pedum, marking the threshold when animals could create 3-dimensional vertical burrow systems. Rusophycus world spanned from 536 to 521 million years ago, corresponding exactly to the periods when sclerite-bearing animals and brachiopods dominated. Finally, Cruziana world began when trilobites appeared, leaving their distinctive crawling traces across Cambrian sea floors. The cause of the Cambrian explosion remains actively debated, though most scientists agree that multiple interacting factors converged rather than a single trigger mechanism. Environmental changes created more suitable conditions for animal life. Rising atmospheric oxygen levels provided metabolic fuel for active lifestyles, while large increases in oceanic calcium concentrations that preceded the Cambrian period supplied raw materials for shell construction. Some researchers point to expansive continental shelves with numerous shallow lagoons, providing living space for diverse animal communities to coexist and interact. Ecological relationships between species may have triggered a massive coevolution as food webs became more complex, and predator-prey relationships intensified selective pressures. Genetic and developmental innovations provide another compelling explanation. The evolution of Hox-controlled genes, master regulatory genes that control body plan development during embryonic growth, may have provided unprecedented morphological flexibility. These genes act as switches determining which body parts form where along an animal's head-to-tail axis. Mutations in Hox genes can produce dramatic changes in body architecture, potentially enabling the rapid exploration of new body plans during the early Cambrian. Any satisfactory explanation for the Cambrian explosion must account not only for why such massive animal diversification occurred, but also why it happened precisely when it did, rather than earlier or later in Earth's history. Despite decades of research, unresolved questions persist. Scientists still debate whether the explosion truly represented unprecedented evolutionary rates or whether it partly reflects improved fossil preservation and the invention of mineralized shells that are more easily preserved than soft tissues. Some evidence suggests more animal life existed prior to the Cambrian than traditionally recognized, while other radiations occurred later in history, though none matched the Cambrian's scope. The animal diversification that began during the Cambrian continued well into the following Ordovician period, blurring the boundaries of when the explosion actually ended. Most scientists agree, however, that the Cambrian marked a time of unmatched rapid animal evolution and diversification of body forms, a singular event in the 4 billion year history of life on Earth. Reconstructing Earth's geography from 500 million years ago presents one of the most challenging puzzles in geology. No maps existed. No photographs captured these ancient landscapes, and the continents themselves have moved thousands of kilometers from their original positions. Yet through painstaking analysis of rock formations, fossil distributions, and magnetic signatures locked within ancient minerals, scientists have assembled detailed reconstructions of where landmasses sat during the Cambrian period. These maps reveal a world profoundly different from today's familiar configuration, with continents scattered across latitudes and separated by ocean basins that no longer exist. The dominant landmass 500 million years ago was Gondwana, a supercontinent of immense proportions that dwarfed any single continent existing today. Gondwana assembled during the late Neo-Proterozoic through a series of collisions between smaller continental blocks, completing its formation around 550 million years ago, just before the Cambrian period began. By 500 million years ago, this massive continent encompassed what would eventually fragment into South America, Africa, Madagascar, India, Antarctica, and Australia, along with smaller terrains including Arabia and fragments that now form parts of southern Europe. Gondwana straddled the southern hemisphere, extending from equatorial latitude southward to the South Pole. Its southern margin, containing the ancestral components of present-day Antarctica and Australia, lay in polar regions, though crucially, no ice sheets existed there. The warm Cambrian climate precluded polar glaciation. Evidence for Gondwana's configuration comes from multiple geological disciplines working in concert. Matching rock formations provide the most straightforward clues. When geologists examine Cambrian age rocks in Africa and South America, they find identical sequences, the same types of sedimentary layers, deposited in the same order with the same distinctive mineral compositions. These matching sequences make sense only if the continents once sat adjacent to each other, sharing a continuous depositional environment. Fossil distributions reinforce this interpretation. Certain trilobite species appear in Cambrian rocks from both Africa and South America, but nowhere else, indicating these regions shared marine connections during the Cambrian while remaining isolated from other parts of the globe. Paleomagnetic data provide perhaps the most powerful tool for reconstructing continental positions. When igneous rocks crystallize from molten magma, iron-bearing minerals within them align with Earth's magnetic field like tiny compass needles. This alignment becomes permanently locked into the rock as it cools, preserving a record of the magnetic field's orientation at that location and time. By measuring these preserved magnetic orientations in rocks of known age, geologists can determine the latitude where the rock formed. The magnetic inclination reveals how steeply the magnetic field lines intersected Earth's surface, which varies predictably with latitude. Rocks formed near the equator show shallow magnetic inclinations because field lines run nearly horizontal there, while rocks formed at high latitudes show steep inclinations as field lines plunge toward or away from the poles. Applying paleomagnetic analysis to Cambrian age rocks from different continents reveals their ancient latitudes. Studies of African rocks indicate that the northern margin of Gondwana, including what would become North Africa, sat near the equator 500 million years ago. Rocks from the southern portions, comprising present-day Antarctica and southern Australia, yield magnetic inclinations consistent with high southern latitudes, confirming that Gondwana spanned from tropical to polar zones. This north-south orientation helps explain climatic patterns recorded in Cambrian sediments. Tropical carbonate rocks and reefs formed along Gondwana's northern shores, while glacial deposits from earlier Neo-Proterozoic ice ages occur in rocks from its southern regions, demonstrating that these areas occupied polar positions during the cryogenian snowball Earth events. The continued movement of tectonic plates throughout the Phanerozoic eon has complicated efforts to reconstruct Cambrian geography because continental fragments have been displaced thousands of kilometers from their original positions. Terranes, fault-bounded crustal blocks with geological histories distinct from surrounding regions, have been particularly problematic to place accurately. However, endemic Cambrian fossils provide powerful tools for identifying these displaced fragments' geographic origins. Northern Scotland hosts trilobite and brachiopod species characteristic of Laurentia rather than Baltica, revealing that this portion of the British Isles originated on Laurentia's margin and was later transferred to Europe during the Caledonian orogeny when the Iapetus Ocean closed. Similarly, west-central Argentina's Precordillera terrain contains Laurentian fossils despite sitting within the Andes mountain chain, demonstrating that this block rifted from Laurentia's margin and travelled across the Iapetus Ocean before colliding with Gondwana. Eastern Newfoundland yields Baltica-type fossils, while southern Mexico's Oaxaca terrain preserves Gondwanan assemblages, each indicating transport from their original continental margins. Another consequence of continued plate motion has been the formation of massive mountain ranges at collision sites, subjecting Cambrian rocks to intense deformation. Pressure and heat generated during these collisions have folded, faulted and metamorphosed significant volumes of Cambrian strata, particularly from outer continental margins and slopes where sediments accumulated in thick sequences vulnerable to tectonic disruption. The Appalachian Mountains, for instance, preserve intensely deformed Cambrian rocks that accumulated on Laurentia's eastern margin before the continent collided with various terrains during the Paleozoic. Unraveling these deformed sequences to understand their original depositional settings requires careful structural analysis and regional geological mapping. An additional complication arises from the simple fact that no oceanic crust older than the Mesozoic era survives in today's ocean basins. Most pre-Mesozoic oceanic deposits that accumulated in deep water environments have been destroyed through subduction as oceanic plates descended into Earth's mantle at convergent plate boundaries. This means the geological record of Cambrian deep ocean environments is essentially absent. What survives consists almost entirely of continental margin deposits that escaped subduction. The Iapetus Ocean that separated Laurentia from Gondwana and Baltica no longer exists. The oceanic crust that once floored this basin has been completely consumed, leaving only scattered fragments of its margins preserved in the Appalachian and Caledonian mountain belts. Despite these challenges, the integration of paleomagnetic data, fossil distributions, sedimentary facies analysis, and structural geology allows remarkably detailed reconstructions of Cambrian paleogeography. The emerging picture shows a world of scattered continents surrounded by vast oceans, with Gondwana dominating the southern hemisphere, Laurentia straddling the equator, and smaller landmasses, Baltica, Siberia, and various microcontinental blocks, distributed across mid to high latitudes. This geography, so profoundly different from the present day, created the environmental conditions and biogeographic barriers that shaped the evolution and distribution of Cambrian life. The oceans that covered Earth 500 million years ago bore little resemblance to modern seas. They dominated the planet to an extent difficult to grasp from our contemporary perspective, where continents rise prominently above sea level and occupy substantial portions of the globe's surface. During the Middle Cambrian, sea levels stood dramatically elevated, perhaps 100 to 150 meters higher than present-day measurements. This immense rise in ocean volume, driven by multiple converging factors, flooded continental margins worldwide and created vast shallow water, environments that covered regions now exposed as dry land. The flooding resulted partly from the continued melting of Neoproterozoic ice sheets, those final remnants of the cryogenian snowball Earth glaciations that had released their grip on the planet between 650 and 635 million years ago. As these massive ice volumes transformed from solid to liquid, they transferred water from frozen continental surfaces into ocean basins, raising global sea level. But glacial melting alone cannot account for the dramatic marine transgression that characterized the Cambrian. Additional factors contributed significantly. The breakup of the supercontinent Rodinia created new mid-ocean ridge systems where oceanic crust formed as tectonic plates pulled apart. These ridges, composed of hot, buoyant rock rising from Earth's mantle, displaced ocean water upward and outward, forcing it onto continental shelves and interiors. The elevated temperatures of the Cambrian period also played a crucial role. Without polar ice caps to lock water away in frozen form, and with average global temperatures hovering around 22 degrees Celsius, substantially warmer than today's 14-degree average, thermal expansion increased ocean volume. Warmer water occupies more space than cooler water due to decreased density, contributing additional rise to sea level beyond what melting ice alone could produce. The result was extensive marine flooding across all continents. Laurentia, straddling the equator, found much of its interior submerged beneath shallow epicontinental seas. These inland oceans, connected to the open Panthalassa through narrow straits and passages, created protected environments where carbonate platforms flourished. Thick sequences of limestone and dolomite accumulated across millions of square kilometers. Built from the shells of countless organisms and from chemical precipitation as warm tropical waters became supersaturated with dissolved calcium carbonate. The Great American Carbonate Bank, stretching from present-day California through Nevada, Utah, and into the Canadian Rockies, represents one of the most extensive carbonate platforms in Earth's geological record. Gondwana similarly experienced massive flooding along its margins, though the continental interior, comprising the ancient cratons of Africa, South America and Antarctica, stood above sea level. Vast, shallow seas lapped against these shores and penetrated deep into embayments and rifts cutting through the landmass. The northern margin of Gondwana, facing the Iapetus Ocean, hosted particularly extensive shallow water environments where diverse marine communities thrived in warm, nutrient-rich waters. Even Baltica, positioned at higher southern latitudes in cooler waters, suffered significant marine transgression. Though its carbonate deposition remained limited compared to tropical Laurentia, shallow seas flooded across the low-lying topography that characterized this craton. The absence of significant mountain ranges meant that seawater could spread widely across the continental surface, with minimal topographic barriers to restrict its advance. Sedimentary sequences from Baltica preserve evidence of these transgressive events in thick accumulations of sandstone and shale representing coastal and shallow marine environments. The chemistry of Cambrian oceans differed substantially from modern seawater in several critical respects. Calcium concentrations likely exceeded present-day levels, driven by accelerated weathering of continental rocks. The warm climate, combined with the absence of vegetation to stabilize soils and slow erosion, meant that rain falling on exposed bedrock dissolved minerals rapidly and carried them into adjacent seas. The Transgondwanan supermountain, that vast orogenic belt stretching across East Africa, shed enormous quantities of sediment and dissolved calcium into surrounding waters. This calcium influx provided the raw material enabling the explosion of shell-building organisms during the early Cambrian, trilobites, brachiopods, mollusks, and countless other groups that constructed mineralized skeletons for protection, support, and attachment. Sulfate concentrations in Cambrian seawater also differed from modern oceans, though the direction and magnitude of this difference remain subjects of active research. Some geochemical models suggest lower sulfate levels than today, potentially affecting the metabolic pathways available to bacteria living in oxygen-depleted seafloor sediments. Others propose that sulfate levels fluctuated considerably throughout the Cambrian in response to changing rates of continental weathering, volcanic outgassing, and biological sulfur cycling. These variations would have profound implications for ocean chemistry, influencing everything from the precipitation of minerals to the preservation of organic matter in sediments. Magnesium to calcium ratios in seawater represent another critical chemical parameter that affects which minerals precipitate from solution. Modern oceans maintain relatively high magnesium concentrations compared to calcium, favoring the precipitation of aragonite, a form of calcium carbonate, over calcite. Cambrian oceans, by contrast, likely featured lower magnesium to calcium ratios, creating what geochemists call calcite seas, where calcite formed preferentially. This distinction matters because different organisms construct shells from different carbonate minerals. and the availability of these minerals in seawater influences which skeletal architectures prove viable. Ocean temperatures during the Cambrian exhibited patterns strikingly different from the modern world. Isotopic analyses of calcium carbonate fossils from Cambrian rocks provide direct evidence for seawater temperatures, revealing that even high-latitude regions experienced remarkably mild conditions. Research published in Nature, examining oxygen isotopes from conodonts and other marine organisms, indicates that Cambrian oceans maintained temperate conditions across broad geographic ranges. The absence of polar ice caps meant that temperature gradients from equator to poles were far less steep than today, creating a more thermally uniform ocean system. The warm conditions extended deep into the water column. Modern oceans feature sharp thermoclines, boundaries separating warm surface waters from cold deep waters that restrict vertical mixing and create distinct layered structures. Cambrian oceans, by contrast, likely exhibited weaker thermal stratification due to the absence of frigid polar waters sinking to abyssal depths. Without cold, dense water forming at high latitudes and cascading downward to fill ocean basins, the temperature difference between surface and deep waters remained relatively modest. This more uniform temperature structure would have affected ocean circulation patterns, biological productivity, and the distribution of dissolved oxygen throughout the water column. Salinity patterns in Cambrian seas also differed from modern oceans, though reconstructing ancient salinity proves challenging. Studies of fluid inclusions, tiny pockets of seawater trapped within mineral crystals as they formed, suggest that overall marine salinity remained relatively stable over Phanerozoic time, hovering near modern values around 35 parts per thousand. However, regional variations certainly existed, particularly in restricted basins and epicontinental seas, where evaporation concentrated dissolved salts, or where freshwater influx from rivers diluted seawater. The extensive shallow seas flooding continental interiors created ideal conditions for such salinity variations, with landlocked basins potentially becoming hypersaline while coastal regions near river mouths maintained lower salinities. Ocean circulation during the Cambrian responded to the distinctive continental configuration and thermal structure of the period. Modern ocean circulation is driven primarily by thermohaline circulation, the global conveyor belt powered by density differences created when cold, salty water sinks at high latitudes and spreads through deep ocean basins before eventually upwelling in other regions. In the Cambrian world, with its more uniform temperatures and absence of polar cooling, thermohaline circulation operated differently, if at all. Wind-driven surface currents likely dominated ocean circulation, transporting water masses across latitudes and creating gyres, large rotating current systems, in the major ocean basins. The Panthalassa Ocean, that vast expanse of water surrounding the scattered continents, would have developed circulation patterns comparable in some respects to the modern Pacific. Trade winds near the equator pushed surface waters westward, while westerlies at mid-latitudes drove waters eastward, creating subtropical and subpolar gyres. However, the absence of meridional barriers, north-south continental boundaries that block east-west water movement, meant that Cambrian gyres could extend farther around the globe than modern oceanic gyres, which are constrained by continental margins. The elevated sea levels created extensive shallow epicontinental seas that profoundly influenced marine ecosystems and sediment deposition. These inland oceans, sometimes hundreds of kilometers from the nearest open ocean connection, created unique environmental conditions. Water residence times, the average duration water remained within a basin before being exchanged with the open ocean, could extend to years or even decades in large epicontinental seas, allowing local environmental conditions to diverge substantially from oceanic norms. Temperature extremes, both seasonal and daily, exceeded what organisms experienced in the thermally buffered open ocean. Salinity fluctuations, nutrient concentrations, and turbidity all varied more widely in these restricted settings than in open marine environments. These shallow seas also served as massive sediment traps, accumulating thick sequences of limestone, sandstone, and shale that now constitute much of the Cambrian rock record preserved on continents. The slow water circulation within epicontinental seas promoted the settling of fine-grained sediments that remained suspended in the more energetic open ocean. This efficient sediment capture meant that relatively little terrigenous material, eroded rock fragments from continents, reached the deep ocean basins, helping explain why Cambrian deep-water deposits are so rare in the geological record. Oxygen levels in Cambrian oceans varied dramatically with depth and location, creating a complex three-dimensional structure that profoundly influenced where different organisms could survive. Surface waters in productive regions, where photosynthesizing cyanobacteria and algae generated oxygen as a byproduct of converting sunlight into chemical energy, maintained relatively high dissolved oxygen concentrations adequate to support diverse animal communities. However, atmospheric oxygen levels during the Cambrian remained substantially below modern values, perhaps 12 to 15% compared to today's 21%, meaning that even well-oxygenated surface waters contained less dissolved oxygen than modern seas. Below the sunlit surface zone, oxygen concentrations declined sharply. The warm Cambrian climate resulted in lower oxygen solubility in seawater. Warm water holds less dissolved gas than cold water, creating an additional challenge for marine organisms. More critically, the decay of sinking organic matter consumed oxygen as bacteria broke down dead plankton, fecal pellets, and other biological debris raining down from productive surface waters. This oxygen consumption created oxygen minimum zones at intermediate depths, where dissolved oxygen concentrations dropped to extremely low or even zero levels. Recent geochemical evidence suggests that early Cambrian oceans featured modern-type oxygen minimum zones, with both inner shelf and outer shelf environments experiencing pervasive oxygenation in surface and near-surface waters, but periodic anoxia, complete absence of dissolved oxygen, at intermediate depths. This redox structure differs from earlier models proposing uniformly anoxic deep oceans. Instead, the emerging picture shows a highly dynamic system where oxygen levels fluctuated spatially and temporally in response to changing rates of biological productivity, ocean circulation, and organic matter delivery to seafloor sediments. The deep ocean itself likely remained largely anoxic and ferruginous, containing dissolved iron, but little or no oxygen, throughout much of the Cambrian. Without cold, oxygen-rich polar waters sinking to abyssal depths and ventilating deep basins, the lower levels of the ocean became stagnant repositories where oxygen could not penetrate. Iron dissolved from seafloor sediments under these reducing conditions accumulated in deep waters, creating ferruginous conditions documented by iron, speciation data from black shales deposited in deep water settings. These oxygen-depleted conditions profoundly affected the preservation of organic matter and the formation of exceptional fossil deposits. When organic-rich sediments accumulated in anoxic waters, the absence of oxygen prevented aerobic bacteria from decomposing soft tissues. This created the conditions for Lagerstätten formation, those remarkable fossil deposits like the Burgess Shale and Chengjiang Biota that preserve soft-bodied organisms in exquisite detail. The same anoxic conditions that killed bottom-dwelling organisms through oxygen starvation also prevented their decay, allowing mineralization processes to replace delicate tissues with minerals before they could decompose completely. The restricted circulation in epicontinental seas amplified these oxygen gradients. Large, shallow inland seas with limited connections to the open ocean could become severely oxygen depleted in their deeper central regions while maintaining well-oxygenated conditions along their margins. Seasonal variations in temperature and biological productivity drove oscillations between oxic and anoxic conditions, creating environments where only specially adapted organisms could survive. Some Cambrian animals evolved the ability to tolerate low oxygen concentrations, occupying ecological niches unavailable to oxygen-dependent competitors. Nutrient distributions in Cambrian oceans responded to both ocean circulation patterns and the massive influx of weathering products from eroding continents. Rivers draining the Transgondwanan supermountain and other mountain belts carried dissolved phosphorus, nitrogen, iron, and other essential nutrients into coastal waters. These nutrients fueled explosive phytoplankton blooms that formed the base of marine food webs, supporting the diverse animal communities preserved in Cambrian fossil deposits. However, excessive nutrient loading could trigger eutrophication, a condition where rapid phytoplankton growth depletes dissolved oxygen as dead algae decompose, creating the anoxic bottom water conditions documented in many Cambrian sedimentary sequences. Continental weathering rates varied through the Cambrian in response to changing climate, sea level, and the continued evolution of the landscape following the breakup of Rodinia. Periods of enhanced weathering increased the delivery of calcium, magnesium, strontium, and other ions to the oceans, directly influencing seawater chemistry and the mineralogy of carbonate rocks, precipitating from solution. The strontium isotope ratio in marine carbonates, specifically the ratio of strontium-87 to strontium-86, rose during the early Cambrian, indicating increased weathering of continental silicate rocks that contain relatively high proportions of the radiogenic strontium-87 isotope. This enhanced weathering correlates temporally with the Cambrian explosion, suggesting that increased nutrient delivery to the oceans may have facilitated the radiation of animal life by boosting marine productivity. The air that enveloped Earth 500 million years ago would have suffocated most modern animals within minutes. Atmospheric oxygen concentrations during the Middle Cambrian hovered somewhere between 12 and 15% of the atmosphere, substantially below the 21% that characterizes the present day. This seemingly modest difference had profound implications for life, constraining body sizes, limiting metabolic rates, and shaping the evolutionary trajectories of every animal that drew breath from Cambrian seas. Yet paradoxically, these oxygen levels represented a dramatic increase from earlier periods, rising steadily from the Neoproterozoic through a series of pulses and plateaus that transformed Earth's atmosphere from one hostile to complex life into one capable of supporting it. The journey toward oxygenation began billions of years earlier, shortly after the evolution of photosynthesis. Cyanobacteria, microscopic organisms that harvest sunlight to split water molecules and build organic compounds, began releasing oxygen as a waste product sometime around 2.4 billion years ago during what geologists call the Great Oxidation Event. Before this transition, Earth's atmosphere contained virtually no free oxygen. Any oxygen produced by early photosynthesizers immediately reacted with dissolved iron in the oceans or reduced minerals exposed on land surfaces, preventing its accumulation in the atmosphere. Only after these massive oxygen sinks became saturated after the oceans, dissolved iron precipitated out as banded iron. Formations and continental surfaces became oxidized. Could oxygen begin building up in the air itself even after the Great Oxidation Event? Atmospheric oxygen remained at relatively low levels for nearly 2 billion years. Estimates for mid-Proterozoic oxygen concentrations range from perhaps 1 to 10% of the atmosphere, sufficient to create an ozone layer that shielded the surface from lethal ultraviolet radiation, but inadequate to support large, active animals with high metabolic demands. This prolonged period of atmospheric stability, sometimes called the boring billion, saw little evolutionary innovation and limited diversification of life. Eukaryotic cells, organisms with complex internal structures including nuclei, evolved during this interval, but remained largely microscopic and unicellular. The Neoproterozoic era, spanning from 1000 to 541 million years ago, witnessed renewed increases in atmospheric oxygen. The exact timing and magnitude of this oxygenation remain subjects of active research, but most evidence points to significant rises occurring in two main pulses. The first, around 800 to 750 million years ago, may have triggered or been triggered by the Sturtian glaciation, the earlier of the two snowball Earth events that nearly froze the planet solid. The second pulse occurred after the Marinoan glaciation ended around 635 million years ago, during the Ediacaran period, when the first complex multicellular animals appeared. By the beginning of the Cambrian at 538.8 million years ago, oxygen levels had risen to approximately 10 to 14% of the atmosphere, still well below modern concentrations, but sufficiently elevated to cross critical thresholds, enabling animal diversification. Recent research published in the Proceedings of the National Academy of Sciences reveals that these oxygen levels did not remain static throughout the Cambrian, but instead fluctuated in pulses, with periods of elevated oxygenation alternating with intervals of decline. These pulses correlate temporally with major radiations of animal life, suggesting that rising oxygen provided the metabolic fuel necessary for evolutionary innovations. The relationship between oxygen and animal evolution operates through multiple mechanisms. Most fundamentally, aerobic respiration, the metabolic pathway that animals use to extract energy from food molecules, requires oxygen as the final electron acceptor in a chain of chemical reactions occurring within mitochondria. This process yields far more energy per glucose molecule than anaerobic pathways, enabling active lifestyles, rapid movement, and complex behaviors impossible under low oxygen conditions. Animals living at 12 to 15% atmospheric oxygen faced metabolic constraints that modern animals do not encounter, limiting how large they could grow and how energetically they could behave. Body size in particular correlates strongly with oxygen availability. Larger animals require more oxygen to sustain their greater tissue volumes, but the rate at which oxygen can diffuse from respiratory surfaces, gills in aquatic animals, lungs or tracheae in terrestrial ones, into tissues scales differently than body volume. As animals grow larger, the surface area available for oxygen uptake increases more slowly than the volume of tissue requiring oxygenation, creating a size threshold beyond which oxygen supply cannot meet metabolic demand. This constraint operates especially severely in aquatic environments where dissolved oxygen concentrations depend on atmospheric partial pressure. Lower atmospheric oxygen results in lower dissolved oxygen in seawater, restricting the maximum sizes aquatic animals can achieve. The warm Cambrian climate intensified this oxygen limitation. Warmer water holds less dissolved gas than cooler water, meaning that even if atmospheric oxygen concentrations had matched modern levels, the elevated sea surface temperatures characterizing the Cambrian, perhaps 28 to 38 degrees Celsius in tropical regions compared to modern averages of 26 degrees Celsius, would have reduced dissolved oxygen concentrations in shallow marine waters. The combination of lower atmospheric oxygen and reduced oxygen solubility in warm waters created particularly challenging respiratory conditions for Cambrian marine animals. Despite these constraints, Cambrian animals achieved remarkable diversity and complexity, suggesting they had evolved physiological adaptations enabling them to thrive under lower oxygen conditions than would support equivalent modern forms. Some researchers propose that Cambrian animals possessed more efficient oxygen extraction systems, higher blood oxygen carrying capacities, or metabolic pathways optimized for lower oxygen availability. The prevalence of arthropods during this period may reflect advantages conferred by their respiratory systems. Many aquatic arthropods rely on diffusion across thin gill surfaces with high surface area to volume ratios, enabling efficient oxygen uptake even when dissolved oxygen concentrations remain modest. Scientists reconstruct ancient atmospheric oxygen levels through multiple independent proxies preserved in sedimentary rocks. Charcoal provides perhaps the most direct evidence for oxygen concentrations on land. Wildfires cannot spread when atmospheric oxygen drops below roughly 15%, and the complete absence of charcoal in rocks older than the Devonian period suggests that oxygen remained below this threshold throughout the Cambrian. Iron speciation in marine sediments offers another powerful tool. The relative proportions of different iron minerals, particularly the ratio of highly reactive iron to total iron, reveal whether bottom waters contained dissolved oxygen or remained anoxic. These analyses consistently show that Cambrian oceans featured oxygen minimum zones at intermediate depths, while surface waters maintained adequate oxygenation to support diverse animal communities. Carbon isotope ratios in marine carbonates provide additional constraints. When photosynthetic organisms bury organic carbon in seafloor sediments, they preferentially incorporate the lighter carbon-12 isotope, leaving seawater enriched in the heavier carbon-13 isotope. This enrichment becomes recorded in carbonate minerals precipitating from that seawater. Larger carbon isotope excursions, sharp increases in carbon-13 ratios, indicate periods of enhanced organic carbon burial, which removes carbon from the ocean atmosphere system and allows oxygen to accumulate. Several such excursions punctuate the Cambrian rock record, correlating with the timing of major animal radiations. The pulses of oxygenation documented in Cambrian rocks reflect complex feedbacks between life and the environment. The evolution of bioturbation, animals burrowing through seafloor sediments, fundamentally altered the cycling of nutrients and organic matter. Before animals began churning sediments, organic-rich layers accumulated at the seafloor water interface, where bacterial decomposition consumed oxygen and released nutrients. Bioturbating animals mix these layers, distributing organic matter deeper into the sediment column, where different bacterial communities with different metabolic pathways could process it. This mixing may have enhanced the efficiency of organic carbon burial, allowing more organic matter to escape bacterial decomposition and become permanently sequestered in sediments. Each mole of organic carbon buried represents 1 mole of oxygen released into the ocean atmosphere system, the reverse of the photosynthetic reaction that created the organic matter. Enhanced burial rates during the Cambrian thus drove atmospheric oxygen upward, creating positive feedbacks where rising oxygen enabled larger, more active animals that could burrow more deeply and efficiently, further enhancing burial rates. These feedbacks may explain the characteristic pulses seen in oxygen proxy records, where periods of rising oxygen triggered biological innovations that further accelerated oxygenation. Climate itself influenced atmospheric oxygen through multiple pathways. Warmer temperatures accelerated chemical weathering of continental rocks, particularly the breakdown of phosphate-bearing minerals. Rivers carried this dissolved phosphorus into coastal waters, where it fueled phytoplankton blooms that fixed carbon dioxide into organic matter through photosynthesis. When this organic matter sank and became buried in sediments, it removed carbon from the active carbon cycle while releasing oxygen. The massive erosion of the Transgondwanan supermountain provided particularly intense phosphorus fluxes during the early Cambrian, potentially explaining the timing of oxygen pulses that correlate with the Cambrian explosion. Volcanic activity exerted opposing influences on oxygen levels. The breakup of Rodinia and assembly of Gondwana generated extensive volcanism along new plate boundaries, releasing vast quantities of carbon dioxide, sulfur dioxide, and other gases into the atmosphere. These emissions increased atmospheric carbon dioxide concentrations to perhaps 15 to 20 times pre-industrial levels. Estimates range from 4,000 to 8,960 parts per million, compared to the pre-industrial baseline of 280 parts per million. This elevated carbon dioxide created intense greenhouse warming while simultaneously consuming oxygen through oxidation reactions. With volcanic gases and freshly exposed rock surfaces, the interplay between oxygen-producing and oxygen-consuming processes created a dynamic atmosphere that fluctuated considerably throughout the Cambrian, rather than rising smoothly to modern levels. Research examining carbon and sulfur isotopes from multiple locations worldwide reveals at least 5 distinct oxygen pulses occurring between 524 and 514 million years ago. each representing approximately 50% increases or decreases relative to baseline Cambrian oxygen levels. These fluctuations, though enormous in relative terms, occurred within the constrained range of perhaps 10 to 18% atmospheric oxygen, never approaching the 21% that characterizes the modern atmosphere. Each pulse of oxygenation corresponded with local increases in biodiversity preserved in the fossil record, while oxygen declines associated with elevated extinction rates. Between 521 and 522 million years ago, one pulse coincided with the appearance of numerous shelled animals, including the first trilobites and bivalved arthropods. Several million years later, another oxygen spike aligned temporally with the rise of large predatory arthropods and increased evidence of predatory behaviors recorded as bite marks and damaged shells in fossil assemblages. The Cambrian Explosion, far from representing a singular event driven by steadily rising oxygen, unfolded in spurts, rises and falls that tracked the volatile oxygenation of shallow marine environments. The most dramatic oxygenation event occurred near the end of the Cambrian, around 500 million years ago, during what geologists call the Steptoean positive carbon isotope excursion, or SPICE. Carbon and sulfur isotope mass balance models indicate this event added approximately 19 x 10^18 moles of oxygen to the atmosphere through enhanced burial of organic carbon and pyrite in marine sediments. Starting from initial atmospheric concentrations between 10 and 18%, this pulse may have elevated oxygen to between 20 and 28%, approaching or even temporarily exceeding modern levels. The SPICE event lasted several million years and left its signature in rocks worldwide as a pronounced positive excursion in carbon-13 ratios, indicating massive organic carbon burial, paired carbon isotope measurements from carbonate rocks and organic matter through the SPICE interval reveal an approximately 2 per mil increase in biological fractionation, the preferential uptake of carbon-12 by photosynthesizing organisms, consistent with rising atmospheric oxygen. The SPICE was followed by increased plankton diversity, possibly relating to changes in macro and micronutrient abundances in increasingly oxygenated marine environments. These ecologically diverse plankton groups provided new food sources for animal populations, expanding into progressively more ventilated marine habitats during the subsequent Ordovician period. Recent, comprehensive analyses synthesizing data from black shales deposited throughout the Paleozoic era have refined understanding of when Earth's oceans finally achieved modern oxygenation levels. Contrary to earlier hypotheses proposing that the Cambrian explosion was triggered by atmospheric oxygen rising to near-modern concentrations, the evidence now indicates only modest increases occurred during the early Cambrian. Cambrian animals likely did not require as much oxygen as scientists previously believed, and the minor increases in oxygenation, perhaps just enough to cross critical ecological thresholds, proved sufficient to drive the dramatic changes in animal ecology recorded in the fossil record. Most critically, oxygen levels in the deep ocean did not approach modern concentrations until approximately 140 million years after the Cambrian explosion, around 400 million years ago during the Devonian period. This timing coincides precisely with the appearance of large forests on land, whose roots and associated fungi dramatically accelerated rock weathering, while their tissues provided vast new sources of organic matter for burial in sediments. The full oxygenation of Earth's oceans to near-modern levels thus represents a protracted process, spanning nearly 150 million years from the Cambrian explosion to the Devonian greening of continents. The atmospheric oxygen present 500 million years ago, hovering around 12 to 15%, represented a critical threshold, sufficient to support diverse animal life in shallow, well-mixed marine environments, while remaining inadequate to fully oxygenate deep ocean basins or support the largest body sizes that would evolve later under higher oxygen regimes. This intermediate state shaped the ecology, physiology, and evolutionary trajectories of Cambrian organisms in profound ways that continue reverberating through the history of life. Among all the creatures that populated Cambrian seas, None achieved greater success or left a more abundant fossil record than trilobites. These armored arthropods, with their distinctive three-lobed bodies, divided longitudinally into a central axis flanked by lateral pleural regions, dominated marine ecosystems from their first appearance around 521 million years ago until their final extinction at the end of the Permian period 252 million years ago. During the Middle Cambrian, our 500 million year focal point, trilobites had already radiated into hundreds of species occupying virtually every marine habitat from sunlit shallows to dimly lit continental slopes. The name trilobite derives from this characteristic three-part body division, visible when viewing the animals from above. But equally distinctive was their segmentation along the head-to-tail axis, dividing each individual into three main regions: the cephalon, or head shield at the front, a thorax composed of multiple articulated segments in the middle, and a pygidium, or tail shield, at the rear. This body plan, combining longitudinal lobes with transverse segmentation, created a flexible yet protective architecture that proved remarkably successful across diverse environmental conditions. The cephalon housed the animal's sensory organs, brain, and mouth. Most trilobites possessed compound eyes, sophisticated visual organs composed of multiple individual lenses called ommatidia, each capturing a portion of the visual field. These eyes, positioned on raised areas at the sides of the head shield, provided trilobites with broad fields of view, enabling them to detect predators, locate prey, or identify potential mates. The lenses themselves consisted of calcite crystals, the same mineral forming their exoskeletons, arranged in precise geometric patterns that minimized optical distortions. Some trilobite species possessed hundreds of lenses in each eye, creating visual systems rivaling those of modern insects and crustaceans in complexity. The evolutionary significance of trilobite eyes cannot be overstated. These represent the earliest known examples of complex vision in the animal kingdom, predating all other compound eyes in the fossil record. Their sudden appearance during the early Cambrian, fully formed and sophisticated, suggests that vision evolved rapidly once the selective advantages became apparent. In the arms race between predators and prey that characterized the Cambrian explosion, the ability to see, to detect movement, judge distances, and navigate complex three-dimensional environments conferred enormous advantages to those organisms that possessed it. Not all trilobites, however, relied on vision. Some species living in deep waters, where sunlight could not penetrate, possessed reduced eyes, or lacked them entirely, having evolved blindness as their ancestors colonized lightless environments. These eyeless forms navigated through other senses, touch, smell, or detection of water movements and vibrations, demonstrating the adaptive flexibility that contributed to trilobite success across such a wide range of habitats. The thorax, that middle section between head and tail, consisted of anywhere from 2 to more than 40 segments, depending on the species. Each segment bore a pair of biramous appendages, 2 branched limbs with an inner walking leg and an outer gill-bearing branch. These appendages served multiple functions simultaneously: locomotion across the seafloor, manipulation of food particles toward the mouth, and respiration through thin gill filaments that absorbed dissolved oxygen from seawater. The segmented construction allowed trilobites considerable flexibility, enabling them to curl up defensively when threatened, enrolling like modern pillbugs with the head and tail shields, meeting to enclose the vulnerable underside. The pygidium, forming the rear of the animal, varied enormously in size and shape across different trilobite groups. Some species possessed tiny pygidia composed of just a few fused segments, while others developed massive tail shields rivaling or exceeding their cephalons in size. These variations reflected different ecological adaptations and phylogenetic relationships, providing paleontologists with diagnostic features for identifying species and reconstructing evolutionary histories. The mineralized exoskeleton that gave trilobites their remarkable fossil preservation consisted primarily of calcite infused into a chitinous organic framework. This biomineralized cuticle provided protection against predators, while remaining light enough to permit active locomotion. Growth, however, presented challenges for organisms encased in rigid shells. Like modern arthropods, trilobites solved this problem through molting, periodically shedding their exoskeletons and secreting new, larger ones. Each molt left behind a complete or nearly complete carapace that could fossilize, meaning that a single individual might contribute multiple specimens to the fossil record over its lifetime. This helps explain the extraordinary abundance of trilobite fossils in Cambrian rocks. Estimates suggest that thousands of molted exoskeletons accumulated for every preserved, soft-bodied organism. The first trilobites appeared in the fossil record at approximately 521 million years ago, defining the base of Cambrian Series 2, Stage 3. Their appearance was both sudden and globally widespread, with diverse species appearing nearly simultaneously on multiple paleocontinents separated by thousands of kilometers of ocean. This abrupt emergence with established diversity, phylogenetic disparity, and biogeographic provincialism initially suggested to many paleontologists that trilobites must have originated much earlier, perhaps during the Precambrian, and that their earlier evolutionary history simply remained undiscovered. In the fossil record, however, comprehensive Bayesian tip dating analyses published in the Proceedings of the National Academy of Sciences have challenged this interpretation. By examining evolutionary rates across hundreds of Cambrian trilobite species using discrete, meristic, and continuous morphological traits, researchers demonstrated that trilobites exhibited constant evolutionary rates throughout the entire Cambrian period. This uniformity in evolutionary tempo suggests that by the time typical Cambrian fossils appear at 521 million years ago, the most explosive phase of the Cambrian radiation had already concluded. The data support a Cambrian origin for trilobites, consistent with trace fossil evidence and molecular clock estimates. The oldest trilobite-like traces, scratch marks and burrows attributable to trilobite appendages, date to the early, Fortunian stage of the Terranuvian series, just slightly older than the first body fossils. The absence of Terranuvian trilobite body fossils likely reflects taphonomic factors rather than genuine absence. Early trilobites may have possessed less heavily mineralized exoskeletons that fossilize poorly, or they may have lived in environments where preservation conditions were unfavorable. The unusual scarcity of exceptional soft tissue preservation sites from the Terranuvian, compared to the abundance of such Lagerstätten in later Cambrian strata, means that even abundant soft-bodied or lightly mineralized organisms from this interval would leave little fossil record. By the Middle Cambrian, our 500 million year focal point, trilobites had already diversified into the major orders that would characterize their 270 million year history. Four primary orders dominated the Cambrian: Redlichida, Tychoparida, Agnostida, and Coronexochida. Each exhibited distinctive morphological features reflecting different ecological adaptations and phylogenetic relationships. Redlichides, for instance, typically possessed large, semicircular cephalons with prominent eyes and relatively small pygidia, adapting them for active crawling across open seafloors. Agnostids, by contrast, featured tiny body sizes, often just millimeters in length, and simplified morphologies with only 2 thoracic segments, suggesting either planktonic lifestyles or highly specialized benthic niches. The Middle Cambrian marked the first major crisis in trilobite evolution. Surviving lineages responded by developing isopagous bodies, where the head shield and tail shield achieved similar sizes, or macropygous forms with enlarged pygidia exceeding the cephalon in size. These architectural changes, combined with thickened cuticles providing better defense against predators, characterized successful Middle and Late Cambrian trilobites. The evolutionary pressure favoring these modifications came from the escalating predator-prey arms race that intensified throughout the Cambrian as larger, more sophisticated predators evolved alongside increasingly well-defended prey. Trilobites exploited an extraordinary range of ecological niches across Cambrian seafloors, from sunlit shallows to deep continental slopes beyond the reach of light. Their feeding strategies varied enormously between species, as evidenced by differences in mouthpart structures, appendage morphologies, and the sediments preserved within their gut traces. Many species functioned as deposit feeders, crawling across the seafloor and sifting through sediments to extract organic particles and microorganisms. Others adopted predatory or scavenging lifestyles, using their appendages to capture and manipulate prey items or tear apart carrion. Some trilobites may have filter-fed, using modified gill structures to strain suspended particles from the water column as they crawled or swam. The geographic distribution of trilobite species provides crucial evidence for reconstructing Cambrian paleogeography. Different continental blocks hosted distinctive trilobite faunas, with species composition varying systematically between paleocontinents. Laurentia, straddling the equator, supported tropical trilobite assemblages dominated by genera like Elrathia, Paradoxides, and Olanellus. Gondwanan shelves hosted different assemblages, while Baltica's higher latitude position resulted in yet another distinctive fauna. These biogeographic patterns, termed realms or provinces by paleobiogeographers, reflect the isolation of different continental shelves separated by deep ocean basins that trilobite larvae could not easily cross. However, some trilobite genera achieved remarkably wide distributions, appearing on multiple paleocontinents thousands of kilometers apart. This cosmopolitanism suggests that certain species possessed larval stages capable of surviving extended periods in the water column, drifting with ocean currents across deep water barriers that confined other species to their natal shelves. The tiny agnostid trilobites, in particular, exhibited global distributions that far exceeded those of larger-bodied forms, supporting interpretations that these millimeter-scale arthropods adopted planktonic lifestyles, spending most of their lives drifting in open waters rather than crawling across seafloors. The late Cambrian marked the beginning of trilobite diversity's apex, with species richness reaching levels that would not be exceeded until the subsequent Ordovician radiation. However, the end Cambrian mass extinction event around 485 million years ago dramatically restructured trilobite communities. Almost all red lichida, including the entire superfamily Olanelloidea, became extinct, along with most other late Cambrian stocks. This extinction coincided with a continuing decrease in Laurentian continental shelf area as sea levels fell, suggesting that major environmental upheaval drove the crisis rather than a singular catastrophic event. The extinction selectivity provides insights into which characteristics determine survival versus extinction. Trilobites with isopagous or macropygous bodies, those within large tail shields, survive preferentially over forms with tiny pygidia. Species with heavily mineralized exoskeletons persisted, while those with thinner cuticles disappeared. These patterns suggest that defensive capabilities against predation, combined with physiological tolerances for changing environmental conditions, determined which lineages crossed the Cambrian-Ordovician boundary to participate. In the subsequent Ordovician radiation, trilobites served an additional crucial function. For modern science, beyond their intrinsic paleontological interest, their abundance, rapid evolution, and wide geographic distributions make them ideal index fossils for biostratigraphy, the correlation of rock layers based on fossil content. Cambrian geologists used trilobite species to subdivide the period into finer time intervals, establishing zones typically spanning just 1 to 3 million years. The successive appearances and disappearances of trilobite lineages provide a relative chronology that allows rocks on different continents to be correlated with precision, even when absolute radiometric dates remain unavailable. The biostratigraphic utility of trilobites extends beyond simple presence-absence data. Evolutionary lineages within trilobite groups show progressive morphological changes through time. Gradual modifications in eye structure, thoracic segment counts, pygidial ornamentation, and globular furrow patterns that allow paleontologists to recognize evolutionary stages within continuous sequences. These evolutionary trends, when calibrated against radiometric dates from volcanic ash layers, provide relative age estimates accurate to within 1 or 2 million years for Cambrian strata worldwide. The exceptional preservation of trilobite fossils in certain deposits reveals details of their soft anatomy rarely visible in the fossil record. The Burgess Shale and similar Lagerstätten preserve delicate gill structures, digestive tracts, antennae, and even possible traces of neural tissue in some specimens. These extraordinary fossils demonstrate that trilobite appendages were biramus, divided into 2 branches, with the inner branch serving as a walking leg tipped with claws for gripping substrates or manipulating food, while the outer branch bore thin filamentous gills for respiration. The gills themselves consisted of dozens of fine lamellae creating large surface areas for gas exchange with seawater, enabling efficient oxygen uptake even in the relatively low oxygen conditions characterizing Middle Cambrian oceans. Trilobite life cycles involved multiple developmental stages recognizable in the fossil record. The earliest stage, called the protaspid, hatched from eggs as tiny organisms less than a millimeter long with unsegmented bodies. These protaspid larvae gradually added segments through successive molts during the meraspid stages, each instar adding 1 or more thoracic segments until reaching the adult complement characteristic of their species. The final holospid stage maintained constant segment numbers through maturity, though individuals continued molting periodically to accommodate growth. Some species exhibit dramatic metamorphosis between life stages, suggesting that larvae and adults occupied different ecological niches, perhaps with planktonic larvae dispersing across ocean basins before settling to the seafloor as benthic juveniles. The success of trilobites as a group, measured by their 270 million year existence, spanning from the early Cambrian through the end Permian extinction, reflects their remarkable evolutionary flexibility. While the basic trilobite body plan remained recognizably consistent throughout their history, endless variations on that theme allowed different lineages to exploit diverse ecological opportunities. Some evolved into efficient burrowers with streamlined bodies and reduced eyes, tunneling through seafloor sediments in search of food. Others became pelagic swimmers, spending their entire lives drifting or actively swimming in the water column. Still others developed elaborate spines, knobs, and projections, creating bizarre morphologies whose functions remain debated. Perhaps defense against predators, perhaps sexual displays, perhaps hydrodynamic adaptations for specialized swimming behaviors. The Ordovician period, following the Cambrian, witnessed trilobites reaching their absolute peak in both morphological disparity and species diversity. New orders, including Phacopida and Trinucleoidea, appeared with body plans radically different from their Cambrian ancestors, occupying reef environments and other ecological niches that earlier trilobites had left unexploited. Bizarre forms evolved eye stalks, elevating their compound eyes above the seafloor for improved predator detection, while other lineages lost eyes entirely as they adapted to life in complete darkness. This Ordovician radiation would mark the last great flowering of trilobite innovation. Subsequent Paleozoic history saw variations on established themes rather than fundamentally new architectural experiments. Yet the biostratigraphic value of trilobites extends beyond their utility as temporal markers. Their distinctive faunal provinces, geographic regions, characterized by unique species assemblages, provide independent confirmation of paleogeographic reconstructions based on paleomagnetic and geological data. When trilobite assemblages from 2 widely separated rock formations share numerous species in common, this suggests those regions occupied similar latitudinal zones with oceanographic connections, permitting larval dispersal between them. Conversely, when contemporaneous formations yield completely different trilobite faunas, despite forming at similar latitudes, this indicates geographic barriers, deep ocean basins, unfavorable currents, or temperature gradients that isolated their respective populations. The Cambrian world at 500 million years ago witnessed trilobites at the height of their initial radiation, having diversified from their first appearance 21 million years earlier into hundreds of species occupying every available marine niche from intertidal zones to abyssal plains. Their compound eyes, articulated exoskeletons, and biramous appendages represented sophisticated adaptations that would persist largely unchanged through subsequent evolutionary history. The basic trilobite architecture proved so successful that later, innovations consisted primarily of variations on established themes rather than fundamental redesigns. Competition with other arthropod groups remained relatively limited during the Middle Cambrian, though diverse arthropods populated Cambrian seas, including the large predatory Anomalocaris, the bizarre five-eyed Opabinia, and numerous smaller forms preserved in Lagerstätten. Trilobites dominated benthic communities in terms of both abundance and biomass. Their mineralized exoskeletons provided superior protection compared to the unmineralized or lightly mineralized cuticles characterizing many other Cambrian arthropods, conferring survival advantages in ecosystems where predation pressure intensified throughout the period. The ecological success of trilobites during the Cambrian established patterns that would characterize marine ecosystems throughout the Paleozoic era. As benthic deposit feeders, predators, and scavengers, trilobites occupied crucial positions in food webs, processing organic matter in seafloor sediments and transferring energy from lower trophic levels to higher ones. Their bioturbation activities, the churning and mixing of sediments through feeding and burrowing, enhanced nutrient cycling, increased oxygen penetration into sediments, and created microhabitats exploited by other organisms. These ecosystem engineering functions meant that trilobites shaped their environments just as their environments shaped their evolution. The transition from Cambrian to Ordovician trilobite faunas, though marked by significant extinction, ultimately gave rise to even greater diversity during the Ordovician radiation. Surviving lineages diversified rapidly to fill ecological niches vacated by extinct forms, while simultaneously exploiting new opportunities created by the expansion of reef habitats and the deepening of epicontinental seas. The Ordovician would see trilobites reaching their absolute apex in morphological diversity and species richness, peaks that would never again be equaled in their remaining 185 million years of existence. At 500 million years ago, trilobites stood at a pivotal moment in their evolutionary history. Behind them lay 20 million years of explosive radiation following their first appearance. Ahead lay the end Cambrian extinction that would eliminate many lineages, followed by the Ordovician radiation that would carry surviving groups to unprecedented diversity. The Middle Cambrian seas they inhabited, warm and oxygen depleted by modern standards, provided the crucible in which these armored arthropods refined the adaptations that would sustain them through hundreds of millions of years of subsequent Earth history, making them one of the most successful animal groups ever to evolve. The Cambrian seas witnessed the birth of a behavior that would forever transform life on Earth. One animal actively hunting, capturing, and consuming another. Before this period, organisms fed on organic particles suspended in water, grazed on microbial mats carpeting the seafloor, or absorbed dissolved nutrients directly from their surroundings. The concept of predation, actively pursuing living prey, subduing it through force, and tearing it apart for consumption, represented a revolutionary innovation that fundamentally restructured marine ecosystems and triggered evolutionary changes cascading through every level of the food web. The fossil record documents this transition with remarkable clarity. Ediacaran organisms, those soft-bodied creatures inhabiting seas before the Cambrian, show no evidence of predatory damage, no bite marks, no missing body parts suggesting attacks, no defensive structures indicating threats from hunters. Their world operated according to different rules, where competition for resources occurred, but violence between organisms apparently did not. This changed abruptly at the dawn of the Cambrian, when animals evolved the anatomical tools necessary for capturing and processing prey: grasping appendages, cutting mouthparts, sophisticated sensory systems for detecting victims, and the neural coordination required to execute complex hunting behaviors. The largest and most fearsome predator prowling Middle Cambrian seas was Anomalocaris, a creature whose very name means abnormal shrimp, a reference to the initial misidentification of its fossilized parts as separate organisms. When paleontologists first encountered Anomalocaris fossils in the Burgess Shale during the early 20th century, they interpreted the various body parts as belonging to different animals. The grasping appendages appeared to be shrimp-like crustaceans. The circular mouth seemed to be a jellyfish, and the body segments looked like sponges or holothurians. Only decades later, when more complete specimens were discovered and carefully analyzed, did scientists recognize that these disparate parts belonged to a single, extraordinary animal. Mature Anomalocaris specimens reached lengths approaching 1 meter, making them giants in Cambrian oceans where most animals measured just centimeters across. The body featured a segmented trunk with lateral lobes extending along each side, flexible, paddle-like structures that undulated in coordinated waves, propelling the animal through the water column with surprising agility for its size. These lobes functioned as swimming appendages, allowing Anomalocaris to cruise above the seafloor rather than crawling across it like most contemporary arthropods. This pelagic lifestyle, actively swimming rather than remaining benthic, represented an advanced ecological strategy, providing access to prey throughout the water column and enabling rapid movement across vast distances in search of food. The head bore the animal's most distinctive features: a pair of large, segmented appendages projecting forward from positions flanking the mouth. These grasping arms, equipped with numerous spines along their inner edges, could flex and curl inward with considerable force. Biomechanical analyses of their articulation patterns indicate these appendages swept toward each other in pincer-like motions, capturing prey between them and drawing victims toward the mouth. The spines, arranged in alternating rows, prevented struggling prey from escaping once caught, creating an effective trap from which few small organisms could break free. The mouth itself represented a remarkable evolutionary innovation, a circular structure composed of multiple plates arranged like the segments of an orange, surrounding a central opening. Each plate bore tooth-like projections on its inner edge. The entire assembly could constrict and dilate, functioning as a combined grasping and crushing device that gripped prey, while the outer edges of the plates worked inward, tearing flesh and breaking shells. Nothing comparable existed in earlier oceans. This represented predatory technology without precedent in the fossil record. Anomalocaris possessed large, compound eyes positioned on short stalks extending from the sides of its head. These eyes, similar in construction to trilobite eyes but larger and potentially more sophisticated, provided stereoscopic vision, enabling the animal to judge distances accurately, a crucial capability for a visual predator that must time its strikes precisely to capture mobile prey. The combination of advanced vision, flexible swimming ability, powerful grasping appendages, and specialized crushing mouthparts established Anomalocaris as the apex predator of Middle Cambrian marine ecosystems, a position it maintained for millions of years. Evidence for what Anomalocaris actually ate has generated considerable scientific debate. For decades, paleontologists assumed this apex predator fed primarily on hard-shelled trilobites, pointing to fossil trilobites bearing circular or W-shaped bite marks that appeared to match the dimensions of Anomalocaris mouthparts. Large coprolites, fossilized feces, containing trilobite fragments and attributed to Anomalocaris based on their size, seem to confirm this interpretation. However, recent biomechanical analyses using three-dimensional digital modeling, finite element analysis, and computational fluid dynamics have challenged this long-standing hypothesis. Research published in Proceedings of the Royal Society B in 2023 demonstrated that Anomalocaris canadensis lacked the structural capability to crush mineralized prey with its frontal appendages. Finite element analysis revealed that certain parts of the appendages, particularly the endites where contact with prey occurred, would have experienced high degrees of plastic deformation, permanent bending, when attempting to crush hard shells. The appendages, though formidable in appearance with their rows of spines, were built for speed and flexibility rather than force. Computational fluid dynamics showed that outstretched appendages produced minimal drag when held in streamlined positions, enabling rapid acceleration bursts to capture fast-moving prey. The oral cone itself, that circular array of plates forming the mouth, consisted of unmineralized tissue that showed no signs of wear or damage, despite being preserved in exceptional detail in Burgess Shale fossils. If Anomalocaris regularly crushed trilobite exoskeletons, its mouthplates should exhibit scratches, chips, or other evidence of contact with hard materials, yet none appears. This absence of wear suggests the animal avoided processing mineralized tissues, instead targeting soft-bodied organisms that required no crushing. The biomechanical evidence, combined with analyses of eye placement, body flap hydrodynamics, and tailfan morphology, indicates that Anomalocaris canadensis functioned as an agile tectonic predator, actively swimming in the well-lit upper water column, rather than cruising along the seafloor hunting benthic prey. Its large compound eyes, positioned on short stalks and containing thousands of individual lenses, provided acute vision optimized for detecting movement in open water. These eyes represented some of the most sophisticated visual systems in the Cambrian, potentially rivaling modern dragonfly eyes in their complexity. Such advanced vision makes sense for a predator hunting fast, mobile prey in three-dimensional space, but seems excessive for an animal simply scanning the seafloor for slow-moving trilobites. If Anomalocaris didn't hunt trilobites, what inflicted those circular bite marks preserved on fossil trilobite specimens? The marks actually match the dimensions of Peytoia mouthparts, a different radiodont species with a more robust oral cone potentially capable of gyrophagus predation. Other large radiodonts, including Amplectobelloa and Ramskeldia, possessed appendage structures and mouth morphologies, suggesting they were better equipped for crushing hard prey than Anomalocaris. This evidence points toward niche partitioning among Cambrian apex predators, with different radiodont species specializing on different prey types and hunting in different ecological zones. Anomalocaris likely targeted soft-bodied animals swimming in the water column, possibly including various worms, early chordates, soft-bodied arthropods, and the countless other unmineralized organisms that populated Middle Cambrian seas, but rarely fossilized. The combination of speed, agility, sophisticated vision, and grasping appendages made it supremely adapted for pursuing such prey through open water. At up to 1 meter in length, comparable to a modern house cat, Anomalocaris dwarfed most contemporary animals, establishing it firmly as an apex predator, despite targeting soft rather than armored victims. The existence of predators like Anomalocaris created intense selective pressures that drove prey organisms to evolve an array of defensive adaptations. The evolutionary arms race between predators and their victims represents one of the most powerful engines of diversification during the Cambrian Explosion, forcing organisms to innovate or perish. The fossil record preserves direct evidence of this struggle in remarkable detail. Bite marks on trilobite carapaces, drilled holes in shells, missing body parts suggesting attacks, and damaged skeletons bearing witness to violent encounters that ended in death. The oldest empirical evidence of a predator-prey arms race dates to approximately 517 million years ago, documented in fossils from South Australia. Researchers examining hundreds of microscopic shells belonging to Lapworthella fasciculata, a tomatide species distantly related to brachiopods, discovered more than 200 specimens bearing holes likely made by a single predator, probably a soft-bodied mollusk or worm. When these fossils were analyzed in relation to their geological ages, a striking pattern emerged. Shell wall thickness increased over time, coinciding precisely with an increase in the number of punctured shells. The prey continuously evolved to strengthen its shell against predation, while the predator simultaneously evolved the ability to pierce increasingly thick armor. This microevolutionary arms race demonstrates, for the first time, that predation played a pivotal role in the proliferation of early animal ecosystems and reveals the rapid speed at which such phenotypic modifications arose during the Cambrian Explosion. The evolution of mineralized shells during the early Cambrian represents one of the most significant defensive innovations in the history of life. Before approximately 541 million years ago, animals possessed soft bodies offering little protection against physical attack. The sudden appearance of shells, scales, spines, and plates at the Cambrian's beginning suggests that predation pressure, or the threat of it, drove organisms to construct protective armor. Calcium carbonate and calcium phosphate shells provided effective barriers against many types of attacks, forcing predators to evolve stronger jaws, more sophisticated hunting techniques, or specialization on soft-bodied prey that remained vulnerable. Spines and tubercles proliferated across numerous animal groups during the Cambrian, creating forests of defensive projections that made prey difficult to grasp or swallow. Some organisms developed elaborate arrays of spines radiating from their bodies, transforming themselves into pincushions that few predators could safely approach. Others evolved thick, sculptured shells with interlocking plates that resisted crushing forces. The diversity of defensive architectures appearing during this period demonstrates that natural selection explored countless variations on the basic theme of protection, with different solutions proving viable in different ecological contexts. Burrowing behavior emerged as another crucial defensive innovation, allowing organisms to escape from the dangerous seafloor surface into the relative safety of sediments. The substrate revolution, the increasingly deep and complex burrows appearing in the trace. Fossil record during the Cambrian reflects animals exploiting the three-dimensional space beneath the sediment-water interface. Deep burrows provided refuges where surface predators could not follow, creating ecological zones where different rules govern survival. The evolution of burrowing capabilities required sophisticated sensory systems for navigating through opaque sediments, muscular systems for excavating tunnels, and respiratory adaptations for surviving in low oxygen conditions within the substrate. Speed represented yet another defensive strategy. Mobile organisms that could detect approaching predators and flee rapidly had better survival prospects than slow-moving or sessile forms. The evolution of articulated exoskeletons in arthropods, combined with jointed appendages powered by striated muscles, enabled rapid locomotion across sea floors or through the water column. Natural selection favored increasingly efficient locomotor systems, driving the refinement of body plans optimized for speed and maneuverability. The intensity of predation appears to have increased dramatically during the Cambrian as new predatory tactics, including shell crushing, emerged. This rise of predation was confirmed by temporal patterns in the median predator ratio at the genus scale in fossil communities covering the Cambrian and Ordovician periods. However, this pattern is not correlated with diversification rate, suggesting that predators did not trigger the large evolutionary radiation of animals during this interval through direct causation. Instead, the role of predators as triggers of diversification may have been limited to the very beginning of the Cambrian explosion. Evidence suggests that predation existed long before the Cambrian's start. The increasingly spiny forms of acritarchs, holes drilled in Cloudina shells from the late Ediacaran, and traces of burrowing to avoid predators all indicate that predation pressure operated during the Precambrian. Hence, the appearance of predation likely was not the trigger for the Cambrian explosion, although it certainly exhibited a strong influence on the body forms that the explosion produced. The crucial difference may have been not the invention of predation itself, but rather its intensification and the evolution of increasingly sophisticated predatory technologies that forced prey organisms to respond. With ever more elaborate defenses, the arms race metaphor implies ever-escalating advances in attack and defense. Though these adaptations come with costs, metabolic expenses for constructing shells, energy devoted to maintaining defensive structures, reduced mobility from heavy armor. Organisms face trade-offs between investment in defense versus reproduction, growth, or other fitness components. Natural selection optimized these trade-offs differently in different ecological contexts, creating the spectacular diversity of body plans characterizing Cambrian faunas. The Burgess Shale and Changjiang biota preserve organisms so bizarre that when paleontologists first encountered them, they struggled to determine which end was the head and which was the tail, which side faced up and which down, or even to which major animal group these creatures belonged. These enigmatic fossils challenged fundamental assumptions about animal body plans and forced scientists to reconsider how evolution explores morphological possibilities during periods of rapid diversification. The Middle Cambrian seas swarmed with experimental body architectures, evolutionary trials that sometimes succeeded for millions of years before vanishing, leaving no descendants in the modern world. Hallucigenia stands as perhaps the most famous example of paleontological confusion leading to spectacular reinterpretation. When Simon Conway Morris first described this creature in 1977, based on specimens from the Burgess Shale, he reconstructed it as walking on rigid spines, while 7 pairs of tentacles waved above its back. This interpretation made the animal appear so surreal that Conway Morris named it hallucigenia, suggesting the hallucinatory quality of its anatomy. The reconstruction showed the creature moving along the seafloor on its spines like stilts, with the tentacles perhaps serving as feeding appendages or sensory organs. This upside-down reconstruction persisted in scientific literature and popular depictions for nearly 2 decades, until new fossil discoveries from China's Changjiang deposits provided specimens with better preserved details. When paleontologists examined these new fossils using improved imaging techniques, they realized Conway Morris had reconstructed hallucigenia inverted. What he interpreted as defensive spines projecting upward were actually paired legs walking along the bottom, while the supposed walking spines were defensive structures protecting the animal's back. The tentacles, it turned out, were legs tipped with claws for gripping substrates, while the spines served as armor-deterring predators from attacking from above. Further revisions followed as even more complete specimens came to light. The head, initially misidentified as the tail, actually bore a pair of simple eyes and a mouth surrounded by a ring of smaller spines. High-resolution scanning electron microscopy revealed traces of a simple gut running the length of the body, with possible evidence of what the animal had eaten preserved as dark organic matter within the digestive tract. These successive reinterpretations transformed hallucigenia from an incomprehensible oddity into a comprehensible, though still unusual, member of the Lobopodian group, related to modern velvet worms that still inhabit tropical forests today. Opabinia presented different interpretational challenges. This creature possessed 5 eyes arranged across the top of its head, a segmented body with lateral lobes resembling those of Anomalocaris, and most bizarrely, a long, flexible proboscis projecting forward from beneath its head. The proboscis terminated in a claw-like structure that apparently functioned as a grasping organ, possibly for capturing small prey or gathering organic particles from sediments. When Harry Whittington first presented his reconstruction of Opabinia at a scientific conference in 1972, the audience reportedly burst into spontaneous laughter. The animal seemed too strange to be real. Yet careful analysis of multiple specimens confirmed every peculiar detail. The 5 eyes were genuine, each consisting of thousands of individual lenses creating compound visual organs. The proboscis was not an artifact of preservation, but an actual anatomical structure, flexible enough to curl downward toward the seafloor and equipped with grasping terminal claws. The body bore resemblances to Anomalocaris, suggesting a possible evolutionary relationship between these bizarre animals. Though Opabinia measured just 7 centimeters long, compared to Anomalocaris' meter-length body. Wiwaxia challenged classification in different ways. This slug-like organism, approximately 5 centimeters long, crawled across Cambrian seafloors covered in an armor of overlapping scales and bearing 2 rows of long, pointed spines projecting upward from its back. The scales themselves consisted of calcified sclerites similar to those found in other early Cambrian animals, suggesting these structures evolved independently multiple times as different lineages converged on similar defensive solutions. The ventral surface, the underside, bore a feeding apparatus consisting of multiple rows of teeth that rasped across organic matter on the seafloor, functioning somewhat like the radula of modern mollusks. Initial interpretations placed Wiwaxia among the mollusks based on these radula-like structures. However, subsequent analyses noted similarities between Wiwaxia's sclerites and those of halkyrids, another group of scale-covered Cambrian animals, as well as possible relationships to annelid worms. Modern phylogenetic analyses using comprehensive morphological datasets have variously placed Wiwaxia within mollusks, annelids, or as a stem group Lophotrochozoan, occupying a position before these major groups diverged. The ambiguity reflects genuine evolutionary relationships, during a time when major animal lineages had not yet established the distinctive features that clearly separate them in modern faunas. Halkyrids represent another group whose anatomy defied easy classification. These slug-like creatures measured up to several centimeters in length and crawled across Cambrian seafloors encased in armor consisting of thousands of tiny scales called sclerites. At each end of the body, front and rear, the animal bore larger, shell-like plates resembling miniature brachiopod or mollusk valves. This combination of features suggested possible evolutionary relationships to multiple modern phyla, creating fierce debates among paleontologists about where halkyrids fit on the animal tree of life. The sclerite armor itself varied in form across the animal's body, with some scales flat and overlapping like roof tiles, while others projected upward as spines or ridges. This regional differentiation in skeletal elements hints at sophisticated developmental programs controlling where and how different structures formed, evidence that even these early animals possessed complex genetic, regulatory systems directing body plan development. The shell-like structures at front and rear may have protected the animal's most vulnerable regions, the head with its feeding apparatus and the posterior, with its excretory and reproductive openings. Modern phylogenetic analyses have suggested that halkyrids and their relatives might represent stem group members of larger clades, occupying evolutionary positions before major groups fully diverged and established their distinctive features. This interpretation makes sense in the context of the Cambrian Explosion, a time when animal lineages were actively diverging and body plans remained fluid, not yet locked into the configurations that would characterize them throughout subsequent history. Organisms occupying these transitional positions naturally exhibit mosaics of features found in multiple descendant groups, making their classification challenging but also scientifically valuable for understanding evolutionary transitions. Dinomitius presented a completely different morphological puzzle. This creature consisted of a long stalk anchored to the seafloor, topped by a calyx, a cup-like structure, surrounded by petal-like bracts. The whole assemblage resembled a flower, and early researchers indeed classified it as a plant or plant-like organism. However, detailed examination revealed an alimentary canal running through the calyx, digestive structures suggesting this was an animal that filtered food particles from water, and musculature indicating the bracts could move. The stalk itself showed internal structure inconsistent with plant tissues but compatible with animal collagen and other proteins. The phylogenetic position of Dinomitius remains uncertain. Some analyses suggest relationships to entoprocts, small filter-feeding animals that today live attached to substrates in marine environments. Others propose connections to more distantly related groups, or suggest Dinomitius represents an extinct stem group lineage with no living descendants. What remains clear is that Cambrian seas supported a far wider range of body architectures and ecological strategies than persist in modern oceans. Nectacaris provided one of the most contentious cases of misinterpretation and reanalysis. Initially described as a chordate based on structures interpreted as a notochord and possible gill slits, Nectocaris seemed to represent one of the earliest known members of the vertebrate lineage. This interpretation placed enormous significance on the fossil, as it would document the early evolution of our own phylum. However, subsequent reanalysis using better preserved specimens revealed that the supposed notochord was actually a gut, and the structures interpreted as gill slits were something else entirely. The revised reconstruction depicted Nectacaris as a cephalopod-like organism, an early mollusk, related to modern squids and octopuses with a streamlined body, large eyes, tentacles for capturing prey, and jet propulsion capabilities for rapid swimming. This reinterpretation, though initially controversial, gained acceptance as additional specimens confirmed the presence of mollusk-like features. The case illustrates how fragmentary preservation and the genuinely bizarre nature of many Cambrian organisms can lead even expert paleontologists to dramatically misinterpret what they're seeing. The prevalence of problematic fossils, organisms that defy classification into modern groups, characterized early interpretations of Burgess Shale and Changjiang faunas. Stephen Jay Gould, in his influential 1989 book Wonderful Life, argued that the Cambrian Explosion produced far greater morphological disparity than exists today, with numerous body plans arising during this interval that have no modern representatives. He suggested that many Cambrian organisms represented separate phyla that subsequently went extinct, leaving the modern world impoverished compared to the experimental richness of Cambrian seas. This interpretation sparked vigorous debate among paleontologists and evolutionary biologists. Critics argued that many supposedly unique Cambrian body plans actually represent stem group members of modern phyla, evolutionary positions along the branches leading to today's major groups, but not yet possessing all the derived features characterizing those groups. Under this alternative view, the Cambrian explosion didn't generate vastly more phyla than survive today. Rather, it established the major lineages whose descendants would diversify throughout subsequent history, and the apparent morphological weirdness reflects our viewing these lineages before they evolved their distinctive, modern characteristics. Modern phylogenetic analyses using comprehensive morphological datasets and, where possible, molecular data from living relatives have largely supported the stem group interpretation. Hallucigenia and related lobopodians now appear as stem group arthropods or close relatives, occupying evolutionary positions near the base of arthropod phylogeny. Anomalocaris and Opabinia, rather than representing separate phyla, cluster as stem group arthropods called radiodonts, a successful lineage that persisted through the Ordovician period before going extinct. Wywaxia likely represents a stem group Lophotrochozoan, related to the common ancestor of mollusks, annelids and brachiopods. Nevertheless, some genuinely strange Cambrian organisms may indeed represent extinct body plans without clear relationships to modern groups. The Vetulicolians, peculiar animals with bipartite bodies featuring a large anterior section and segmented posterior tail, have defied definitive placement despite extensive analysis. Some researchers argue for chordate affinities based on possible gill slits and segmentation, while others see arthropod features or suggest Vetulicolians represent an entirely separate phylum. The exceptional preservation conditions creating Burgess Shale-type Lagerstätten remain somewhat mysterious despite decades of research. Rapid burial in fine-grained sediments certainly played crucial roles, preventing scavengers from destroying carcasses and excluding oxygen that would enable aerobic bacteria to decompose soft tissues. The Burgess Shale formed when catastrophic sediment flows swept down the face of an underwater limestone cliff, carrying organisms living on or near the continental slope into deeper waters where anoxic conditions prevailed. Similarly, the Changjiang fossils accumulated in deltaic environments where storm-generated flows periodically buried seafloor communities beneath layers of mud. However, burial alone cannot fully explain the remarkable preservation of delicate features like eyes, gills, gut contents, and possible neural tissues. Additional chemical processes must have rapidly mineralized or replaced these structures before decay destroyed them. The exact mechanisms remain subjects of active research, with proposed explanations involving early orthogenic mineral precipitation, bacterial mediation of fossilization, or rapid formation of organic films that resist decay. At 500 million years ago, the Middle Cambrian seas hosted this extraordinary menagerie of experimental body plans, predatory innovations, and defensive strategies. The bizarre organisms preserved in Lagerstätten, like the Burgess Shale, represent just a fraction of the total diversity that must have existed. Most soft-bodied animals left no fossil record, and even in exceptional preservation sites, sampling biases favor certain body types and environmental settings over others. Yet despite these limitations, the fossils that survive reveal a world of morphological creativity unmatched in subsequent periods, when evolutionary experimentation gave way to refinement within established body plans. Among the countless arthropods, worms, and bizarre creatures populating Cambrian seas swam organisms that would prove far more significant to human history than their modest sizes and simple anatomies might suggest. These were the earliest chordates, animals possessing a flexible rod of tissue called a notochord running along their backs, and their descendants would eventually give rise to fish, amphibians, reptiles, birds, and mammals, including our own species. At 500 million years ago, however, these protovertebrates remained inconspicuous members of marine communities, small fish-like creatures darting through the water column, feeding on microscopic particles while themselves serving as prey for larger predators. The most famous of these early chordates is Picaia gracilens, discovered in the Burgess Shale, and initially dismissed as a worm before its true significance became apparent. Charles Doolittle Walcott, who collected tens of thousands of Burgess Shale specimens between 1909 and 1924, found several Picaia fossils but classified them as polychaeta annelids, segmented worms, based on their elongated, laterally compressed bodies and apparent segmentation. This identification stood unchallenged for decades, with Picaia occupying an obscure position in the catalogue of Cambrian oddities that filled Walcott's extensive collections housed at the Smithsonian Institution. The reinterpretation came in the 1970s when Simon Conway Morris re-examined Walcott's specimens using improved preparation techniques and microscopy. What previous researchers had interpreted as annelid segmentation actually represented serial muscle blocks called myomeres, V-shaped muscle segments characteristic of chordates. Running along the animal's dorsal midline, Conway Morris identified a dark linear structure, the notochord, that defining feature of the chordate phylum. This flexible rod, composed of fluid-filled cells surrounded by a fibrous sheath, provided structural support while allowing the body to flex from side to side in undulating swimming motions. Picaia measured approximately 5 centimeters in length, with a streamlined body optimized for efficient movement through water. The head bore a pair of tentacles, possibly sensory structures for detecting chemical or mechanical cues in the surrounding water. Behind the head, the body tapered gradually toward a tail equipped with fin-like structures that may have provided additional propulsion or stabilization during swimming. The overall body plan, elongated, laterally compressed, with serial musculature, closely resembled that of modern lancelets or Amphioxus, those small marine animals that represent living examples of the basic chordate body architecture. The significance of this reinterpretation cannot be overstated. If Picaia truly represented an early chordate, then the Burgess Shale preserved direct ancestors, or at least very close relatives, of the vertebrate lineage. Every fish that swam through subsequent oceans, every tetrapod that crawled onto land, every dinosaur that dominated the Mesozoic, and every mammal that inherited the Earth descended from creatures fundamentally similar to Picaia. This small, seemingly insignificant organism swimming through middle Cambrian seas, carried within its genome the developmental programs that would eventually generate backbones, skulls, jaws, limbs, and all the other innovations characterizing vertebrate evolution. However, Pikaia was not alone. The Chengjiang biota in China, slightly older than the Burgess Shale at approximately 518 million years, yielded additional early chordates that provided crucial comparative material. Hycoichthys and Mylloconmingia, both discovered in the 1990s, exhibited features suggesting they were more derived, more anatomically advanced than Pikaia, possibly representing actual vertebrates rather than just chordates. These creatures possessed structures interpreted as gill arches, possible skull cartilages, and what appeared to be simple brains, placing them closer to true fish than to the more primitive body plan exemplified by Pikaia. Hycoichthys, measuring about 2.5 centimeters long, displayed clear segmentation along its body with visible W-shaped myomeres. Behind its head lay a series of gill pouches, approximately 6 to 9 pairs depending on the specimen, where water flowed in through the mouth and out through lateral openings, allowing the animal to extract dissolved oxygen as water passed over respiratory surfaces. This countercurrent exchange system, where water and blood flow in opposite directions across thin gill membranes, represents one of the most efficient respiratory mechanisms in the animal kingdom and characterizes all fish. The anterior end of Hycoichthys featured structures that may represent the earliest evidence of vertebrate cephalic complexity, what appeared to be cartilaginous. Elements surrounding the brain and sensory organs suggested the beginnings of a cranium, that protective housing that would become one of the defining features separating vertebrates from other chordates. The presence of possible otic capsules protecting inner ear structures indicated sophisticated balance and orientation systems, essential for an actively swimming animal that needed to maintain stable positioning in three-dimensional aquatic space. Mylloconmingia, discovered alongside Hycoichthys in the same Chengjiang deposits, exhibited similar features but with subtle anatomical differences that have sparked debate about whether these represent separate species or variants of closely related forms. Like Hycoichthys, Mylloconmingia possessed clear myomeres, creating the characteristic chevron pattern along its flanks, a notochord providing axial support, and what appeared to be a series of gill pouches. The preservation quality in some specimens allowed researchers to identify possible blood vessels, traces of kidney-like organs called nephridia, and even hints of neural tissue within the dorsal nerve cord. The evolutionary significance of these early vertebrates extends far beyond their modest anatomies. Hycoichthys and Mylloconmingia, dated to approximately 525 to 520 million years ago, represent the earliest definitive vertebrate fossils known to science. Their existence during the early Cambrian, just 15 to 20 million years after the period began, demonstrates that the vertebrate lineage diverged from other chordates very early in the Cambrian Explosion, likely during the initial phase of animal diversification. This timing places vertebrate origins squarely within the broader context of the Cambrian radiation, suggesting that the same environmental and ecological factors driving arthropod, mollusk, and other phyla diversification also influenced early vertebrate evolution. The anatomical features preserved in these fossils reveal crucial evolutionary transitions. The gill pouches, for instance, represent a fundamental innovation in respiratory anatomy. Rather than relying solely on diffusion across body surfaces for gas exchange, adequate for very small organisms but insufficient for larger, more active animals, these early vertebrates evolved specialized respiratory structures that greatly increased surface area available for oxygen uptake. The pharyngeal gill slits, supported by cartilaginous or collagenous arches, created a pumping system where muscular contractions drew water into the mouth, forced it past respiratory surfaces, and expelled it through lateral openings. This mechanism provided far more efficient oxygenation than passive diffusion, enabling more active lifestyles and larger body sizes than would otherwise be possible. The possible cartilaginous elements surrounding the brain represented another crucial innovation. A protective cranium, even in rudimentary form, shielded the delicate neural tissue from physical damage while providing structural support for sensory organs. The concentration of sensory structures at the anterior end, eyes for detecting light and movement, olfactory organs for sensing chemical cues, otic capsules for balance and possibly hearing, established the cephalized body plan that characterizes all vertebrates. This concentration of sensory and neural processing capabilities in a distinct head region, combined with bilateral symmetry and directional locomotion, created an efficient architecture for actively foraging animals. The question of whether Hycoichthys and Milocanmingia represent true vertebrates or stem group members occupying evolutionary positions just outside the vertebrate crown group remains debated. The key issue centers on whether these animals possessed neural crest cells and placodes, embryonic cell populations that give rise to many vertebrate-specific features including certain skull elements, pigment cells, and parts of the sensory nervous system. Because soft tissues, like neural crest derivatives, rarely fossilize, paleontologists must infer their presence or absence from skeletal features and anatomical arrangements visible in fossils. The apparent presence of cranial cartilages and sophisticated sensory organs suggests these features were present, supporting classification as true vertebrates. But some researchers prefer more conservative interpretations pending additional evidence. Regardless of their exact phylogenetic position, these early fish-like creatures represent the stock from which all subsequent vertebrates descended. Every innovation characterizing later vertebrate evolution, jaws, paired fins, bony skeletons, lungs, limbs, amniotic eggs, built upon the foundation established by these Cambrian pioneers. At 500 million years ago, in the Middle Cambrian, vertebrates remained relatively minor components of marine ecosystems, far less abundant and diverse than trilobites, brachiopods or other invertebrate groups. Yet within their simple bodies lay the developmental programs and anatomical architectures that would eventually enable their descendants to dominate Earth's oceans, invade freshwater and terrestrial environments, and ultimately achieve cognitive capabilities sufficient to study their own evolutionary origins preserved in rocks 500 million years old. While Cambrian oceans teemed with trilobites, predatory arthropods, and the earliest vertebrates, the continents presented a starkly different picture. At 500 million years ago, terrestrial landscapes remained almost entirely devoid of visible life. No forests covered the hillsides, no grasses carpeted the plains, not even simple mosses or lichens clung to rock surfaces in any abundance. The land existed as a barren realm of exposed bedrock, gravel plains, sand dunes, and mudflats, a harsh, alien environment fundamentally hostile to complex multicellular life. The absence of vegetation created erosion rates far exceeding anything experienced in the modern vegetated world. Without plant roots to bind soil particles together, or vegetation to absorb the kinetic energy of falling raindrops, precipitation washed freely across exposed surfaces, carving deep gullies and transporting vast quantities of sediment toward the oceans. Rivers ran brown with suspended particles, their channels unstable and constantly shifting as seasonal floods rearranged landscapes with each major storm. Alluvial fans spread across lowlands where rivers emerged from upland regions, depositing coarse gravels and sands in braided channel systems that lacked the stability imposed by riparian vegetation in modern environments. The rock cycle operated differently in this vegetation-free world. Chemical weathering, the breakdown of minerals through reactions with water, oxygen, and dissolved acids proceeded rapidly in the warm Cambrian climate, but physical erosion dominated to an extent unknown in later periods. Freeze-thaw cycles in regions experiencing seasonal temperature variations shattered bedrock into angular fragments. Wind-driven sand abraded exposed rock surfaces, polishing and sculpting formations into shapes determined purely by lithology and structural geology rather than by biological factors. Desert pavements formed where wind winnowed away fine particles, leaving behind armor of coarse pebbles and cobbles, protecting underlying sediments. Coastal environments presented the only zones where terrestrial and marine realms intersected, creating transitional habitats where conditions varied wildly between extremes. Intertidal zones experienced twice-daily cycles of submersion and exposure as tides advanced and retreated across gradually sloping shorelines. During high tide, seawater covered these areas completely, bringing dissolved nutrients and marine organisms into contact with terrestrial substrates. At low tide, the same surfaces faced atmospheric exposure, desiccating winds, temperature fluctuations, and the full intensity of solar radiation unfiltered by water. These harsh intertidal conditions, paradoxically, may have provided the first footholds for life attempting to colonize land. Microbial mats, layered communities of cyanobacteria, other bacteria, and possibly simple eukaryotic algae likely established themselves along shorelines where periodic flooding provided moisture and nutrients, while exposure to air remained tolerable for organisms capable of surviving desiccation. Modern microbial mats in similar environments form tough, leathery surfaces that resist erosion and can recover quickly from physical disturbance, suggesting that Cambrian equivalents may have possessed comparable resilience. Evidence for these early terrestrial microbial communities remains sparse and controversial. The problem stems partly from preservation bias. Microbial mats consist of soft tissues that rarely fossilize, and when they do, the resulting structures can be difficult to distinguish from abiotic sedimentary features. Stromatolites, the layered mounds formed by mat-building microorganisms trapping and binding sediment particles, occur abundantly in marine environments throughout the Precambrian and Cambrian, but become problematic to interpret in terrestrial settings where similar structures might form through purely physical processes. The most compelling evidence for Cambrian terrestrial life comes not from body fossils, but from geochemical signatures preserved in ancient soils. Paleosols, fossil soils buried and preserved in sedimentary sequences from Cambrian age deposits in various locations, show patterns of mineral alteration consistent with biological activity. Certain clay minerals form preferentially in the presence of organic acids secreted by microorganisms, while the redistribution of iron and manganese within soil profiles suggests microbially mediated redox reactions occurred. Carbon isotope ratios in organic matter preserved within these paleosols fall within ranges characteristic of photosynthetic organisms rather than abiotic carbon sources, though interpreting these signatures requires careful consideration of potential contamination and diagenetic alteration. Spores representing potential early land plants or their precursors appear in rocks from the Middle to Late Cambrian. Though their interpretation remains debated, these microscopic structures, preserved through their resistant outer walls composed of sporopollenin, a tough organic polymer that resists decay, show morphologies suggesting they functioned as dispersal units for terrestrial or semi-terrestrial organisms. However, distinguishing between spores produced by true land plants versus those from green algae inhabiting freshwater or coastal environments proves challenging when dealing with such simple, ancient forms. The environmental challenges facing organisms attempting to colonize Cambrian continents were formidable and multifaceted. Desiccation posed perhaps the most immediate threat. Aquatic organisms maintain their internal water balance through osmotic regulation, controlling the movement of water and solutes across cell membranes to match the surrounding medium. On land, constant evaporation from exposed body surfaces creates water loss that aquatic adaptations cannot prevent. Organisms lacking specialized structures to retain moisture, impermeable cuticles, stomata that can close to restrict water vapor loss, or the ability to become dormant during dry periods, would desiccate rapidly when exposed to air. Ultraviolet radiation presented another critical barrier. In aquatic environments, water itself provides substantial UV protection, absorbing the most damaging wavelengths within the first few meters of depth. Organisms living on land receive the full intensity of solar UV radiation, which damages DNA, proteins, and cell membranes through photochemical reactions. By the Cambrian period, atmospheric oxygen concentrations had risen sufficiently to generate an ozone layer in the upper atmosphere, which absorbs much of the most dangerous UVC radiation. However, UVA and UVB still reached Earth's surface at intensities requiring protective adaptations, pigments that absorb or reflect UV wavelengths, DNA repair mechanisms to fix radiation damage, or behavioral strategies like sheltering beneath rocks or within soil during peak radiation hours. Temperature extremes challenge potential terrestrial colonists in ways unknown to marine organisms. Oceans maintain relatively stable temperatures due to water's high heat capacity and the mixing that occurs through currents and wave action. Terrestrial environments, by contrast, experience dramatic temperature swings between day and night, especially in regions far from moderating oceanic influences. A rock surface might reach 50 degrees Celsius under direct midday sun, then plummet to near-freezing temperatures during clear nights, as radiative cooling dissipates heat into space. Organisms lacking mechanisms to buffer these thermal fluctuations, insulation, behavioral thermoregulation, or metabolic adaptations enabling survival across wide temperature ranges, would find terrestrial existence impossible. Nutrient acquisition posed challenges of a different sort. Marine environments provide nutrients in dissolved form, allowing organisms to absorb essential elements directly from surrounding water. On land, nutrients exist primarily in solid mineral form within rocks and soils, requiring weathering processes to release them into forms organisms can utilize. Without the extensive root systems and mycorrhizal associations that enable modern plants to mine nutrients from soils, early terrestrial organisms had access only to nutrients dissolved in whatever moisture films existed on rock surfaces or in soil-poor spaces. Reproduction and dispersal. On land, required innovations fundamentally different from aquatic strategies. Many marine organisms release gametes directly into water, where fertilization occurs externally, and currents disperse offspring over wide areas. On land, external fertilization becomes problematic without water to transport gametes, while desiccation threatens any exposed reproductive cells or embryos. Successful terrestrial reproduction demanded either retention of aquatic reproductive stages, requiring organisms to return to water for breeding, limiting their terrestrial ranges to areas near permanent moisture, or evolution of protected reproductive structures like spores, seeds, or eggs with shells preventing desiccation. Structural support presented yet another engineering challenge. Water's buoyancy supports aquatic organisms, allowing relatively delicate structures to function effectively. On land, gravity imposes constant downward force that organisms must resist through rigid support structures. The earliest terrestrial organisms likely remained small and low-growing, either forming mat-like structures spread across substrates or adopting prostrate growth forms that minimized height. The evolution of rigid support tissues, lignified cell walls in plants, exoskeletons in arthropods, became necessary prerequisites for organisms to achieve greater size and vertical stature on land. Gas exchange mechanisms required fundamental redesign for terrestrial life. Aquatic organisms extract dissolved oxygen from water passing over gill surfaces, or absorb it directly through permeable body surfaces. In air, oxygen exists at much higher concentrations than in water, making it more readily available, but requiring different anatomical structures to access it. The evolution of spiracles and tracheal systems in terrestrial arthropods, or stomata and internal air spaces in plants, represented crucial innovations enabling organisms to obtain atmospheric oxygen while minimizing water loss through the same openings. Despite these formidable challenges, evidence suggests that microbial life had indeed established footholds in certain terrestrial environments by the Middle Cambrian. Cyanobacteria, which already dominated marine photic zones and had been producing oxygen through photosynthesis for billions of years, possessed many characteristics pre-adapting them for terrestrial existence. Their tough cell walls provided some protection against desiccation. Many species produce UV-absorbing pigments as protection against radiation damage. The ability to form dormant spores or resistant stages enabled survival through unfavorable periods. These characteristics, evolved originally for survival in variable marine environments, proved fortuitously advantageous for colonizing land. Fungi may have joined bacteria and cyanobacteria among the early terrestrial colonists, though direct fossil evidence remains elusive. Modern fungi play crucial roles in terrestrial ecosystems through their ability to decompose organic matter and form symbiotic associations with plant roots, but their soft tissues rarely fossilize. Molecular clock estimates, extrapolations based on genetic divergence rates between modern fungal lineages, suggest fungi may have colonized land during the Cambrian or even earlier, but these estimates carry substantial uncertainty. Circumstantial evidence supporting early fungal terrestrialization comes from the observation that successful plant colonization of land, which occurred during the subsequent Ordovician and Silurian periods, likely required mycorrhizal partnerships. If fungi had not preceded or accompanied plants onto land, these crucial symbioses could not have formed. The ecological impact of early microbial mats, though limited compared to later vegetation, may have begun the gradual transformation of terrestrial environments. By stabilizing sediment surfaces, mats reduced erosion rates locally, allowing soil development to proceed. Organic acids secreted during metabolism accelerated chemical weathering of underlying minerals, releasing nutrients into developing soils. The organic matter accumulated within and beneath mat communities provided carbon substrates for heterotrophic bacteria, establishing the first terrestrial food webs. Dead mat material contributed to soil organic content, gradually building the complex mixture of mineral particles, organic compounds, and living organisms that characterizes true soils. Rivers and streams provided corridors where aquatic life could penetrate into continental interiors. Freshwater environments, though chemically different from marine habitats, offered continuity of aqueous conditions, enabling aquatic organisms to disperse upstream from coastal regions. By the Middle Cambrian, freshwater ecosystems likely hosted adapted versions of marine groups, perhaps simple arthropods, worms, and algae exploiting resources unavailable to their saltwater relatives. These freshwater pioneers faced their own challenges, including osmotic stress from dilute water, variable flow regimes that could shift from torrential floods to stagnant pools, and temperature extremes more severe than marine environments experienced. Lakes and ponds, where they existed, provided stable aquatic habitats within terrestrial landscapes. However, the Cambrian fossil record yields remarkably few lacustrine deposits, suggesting permanent freshwater bodies remained rare compared to later periods. This scarcity may reflect the absence of vegetation to regulate hydrological cycles. Without plants to absorb rainfall and release it gradually through evapotranspiration, precipitation ran off rapidly into rivers and oceans, rather than accumulating in stable lakes. The lakes that did exist probably occupied structural basins, depressions created by tectonic processes or volcanic activity, rather than the diverse array of lake types characterizing modern continents. The contrast between flourishing marine ecosystems and barren continents during the Cambrian reflects the fundamental difficulty of transitioning from water to land. This transition, one of the most profound in evolutionary history, would not be accomplished by complex animals until the Silurian and Devonian periods, roughly 100 million years after our Cambrian focal point. Plants began their terrestrialization somewhat earlier, during the Ordovician, but remained small and simple for tens of millions of years before developing the structural and physiological innovations enabling forests. At 500 million years ago, the continents waited empty, representing vast unexploited ecological opportunities for any organisms capable of meeting the extreme environmental challenges terrestrial existence imposed. the selective advantages awaiting successful colonists: abundant solar radiation for photosynthesis, atmospheric oxygen for respiration, mineral nutrients weathering from exposed rocks, and freedom from marine predators were enormous. Yet the adaptations required to access these resources proved so demanding that tens of millions of years of evolution would pass before complex terrestrial ecosystems finally emerged. The barren Cambrian continents, hostile though they appeared, represented not permanent barriers but temporary frontiers that life would eventually cross, transforming Earth's surface as profoundly as the Cambrian Explosion had transformed its oceans. The climate system, governing Earth 500 million years ago, bore little resemblance to the familiar patterns characterizing the modern world. Average global temperatures hovered around 22 degrees Celsius, approximately 8 degrees warmer than today's 14-degree mean. No permanent ice sheets crowned either pole, creating what climatologists term a greenhouse world, fundamentally different from the glaciated icehouse conditions that have characterized much of the past 35 million years. This warmth extended from equatorial regions into high latitudes, creating climatic zones so different from their modern equivalents that reconstructing ancient weather patterns requires careful integration of geological evidence, geochemical proxies, and climate modeling. The absence of polar ice represented one of the most striking features of Cambrian climate. Modern Antarctica, buried beneath ice sheets averaging 2 kilometers thick and containing roughly 26.5 million cubic kilometers of frozen water, has no equivalent in the Middle Cambrian. Similarly, the Arctic Ocean, today largely covered by sea ice throughout the year, remained ice-free, with surface waters warm enough to support marine life at latitudes that now experience months of continuous winter darkness. This ice-free world resulted from elevated atmospheric carbon dioxide, concentrations that maintained intense greenhouse warming despite the sun shining approximately 5% less intensely than it does today. Atmospheric carbon dioxide levels during the Cambrian exceeded modern pre-industrial concentrations by factors of 15 to 20, with estimates ranging from 4,000 to 8,160 parts per million, compared to the pre-industrial baseline of 280 parts per million. These extreme greenhouse gas concentrations resulted from multiple factors converging during this period. The breakup of the supercontinent Rodinia and the assembly of Gondwana generated extensive volcanism along new plate boundaries, releasing vast quantities of carbon dioxide through volcanic outgassing. The elevated sea levels that flooded continental margins created extensive shallow carbonate platforms where carbon dioxide dissolved into seawater and precipitated as limestone. But this carbon sequestration proved insufficient to offset volcanic emissions. The warm climate accelerated the hydrological cycle, driving more vigorous evaporation from ocean surfaces and more intense precipitation over land. However, the absence of vegetation to regulate water cycling meant that precipitation patterns differed fundamentally from modern conditions. Without forests to recycle moisture through evapotranspiration, the process by which plants absorb water through roots and release it through leaf stomata, rainfall, ran off rapidly into rivers and oceans, rather than being retained in terrestrial ecosystems. This created seasonal flow regimes more extreme than those characterizing modern vegetated watersheds, with torrential floods during wet seasons, followed by severe droughts when rains ceased. Isotope geochemistry provides the primary tool for reconstructing Cambrian temperatures. When marine organisms construct shells from calcium carbonate, they incorporate oxygen atoms from surrounding seawater into their skeletal structures. The ratio of oxygen-18 to oxygen-16 isotopes in these shells varies predictably with temperature. Cooler waters favor incorporation of the heavier oxygen-18, while warmer waters result in lower oxygen-18 to oxygen-16 ratios. By measuring these isotope ratios in fossil shells from Cambrian rocks and comparing them to known temperature isotope relationships calibrated using modern organisms, paleoclimatologists can estimate ancient ocean temperatures. Research. examining oxygen isotopes from Cambrian conodonts, tiny tooth-like structures from primitive eel-like creatures indicates that even high-latitude regions experienced remarkably mild conditions. Waters at 60 degrees latitude north or south maintain temperatures around 20 to 25 degrees Celsius, warmer than modern tropical seas. This temperature distribution created far weaker equator-to-pole thermal gradients than exist today, reducing the temperature difference driving atmospheric and oceanic circulation. Modern Earth experiences roughly 30 to 40 degrees Celsius difference between equatorial and polar surface temperatures, while Cambrian gradients may have been half that or less. The weakened temperature gradients profoundly affected atmospheric circulation patterns. In the modern climate system, strong temperature contrasts between equator and poles drive vigorous mid-latitude weather systems. The low-pressure cyclones and high-pressure anticyclones that bring variable weather to temperate regions. Cambrian climate, with its more uniform temperature distribution, likely featured weaker mid-latitude storms and more stable weather patterns. The Hadley cells, large-scale atmospheric circulation patterns where air rises near the equator, flows poleward at high altitude, and descends in subtropical regions, probably extended farther toward the poles than they do today, expanding the zone of dry subtropical conditions into higher latitudes. Computer simulations of Cambrian climate, using general circulation models originally developed for modern weather forecasting, but adapted for ancient boundary conditions, confirm these basic patterns. Models incorporating Cambrian continental configurations, elevated carbon dioxide levels, and ice-free polar regions produce warm, relatively uniform temperature distributions with weak equator-to-pole gradients. These simulations suggest that tropical conditions, characterized by warm temperatures, high humidity, and seasonal monsoon rainfall, extended to approximately 60 degrees latitude in both hemispheres. Beyond these tropical zones, subtropical conditions with warm temperatures but lower rainfall dominated through roughly 70 degrees latitude. Only the immediate polar regions, experiencing months of continuous winter darkness, maintained cooler temperatures, though even these areas remained well above freezing year-round. Seasonal variations in Cambrian climate responded to the same astronomical forcing that governs modern seasonality. Earth's axial tilt of approximately 23.5 degrees causes the northern hemisphere to receive more direct sunlight during June through August, while the southern hemisphere tilts away from the sun, with conditions reversing during December through February. This fundamental driver of seasonality operated 500 million years ago just as it does today, creating annual cycles of temperature and precipitation. However, the magnitude of seasonal temperature swings differed substantially from modern patterns. In the modern world, continents in mid to high latitudes experience dramatic seasonal temperature variations, with differences between summer and winter means often exceeding 20 to 30 degrees Celsius in continental interiors far from moderating oceanic influences. Cambrian seasonality, by contrast, remained more muted due to the globally warm climate and weak thermal gradients. High-latitude regions that today freeze solid during winter months maintained above freezing temperatures year-round during the Cambrian, experiencing seasonal cycles between warm and very warm rather than between freezing and mild. Precipitation patterns exhibited stronger seasonality than temperature, particularly in tropical and subtropical regions. Monsoon systems, seasonal reversals in wind direction driven by differential heating of land and ocean, likely operated during the Cambrian, bringing summer rainfall to continental margins while winters remained dry. The extensive shallow epicontinental seas flooding continental interiors created complex regional climate patterns where maritime influences moderated temperature, extremes and enhanced precipitation compared to more continental settings. Ocean circulation during the Cambrian differed fundamentally from modern patterns due to the absence of polar cooling. The modern ocean circulation system operates as a global conveyor belt powered by thermohaline circulation. The sinking of cold, Dense water at high latitudes drives deep water flow that spreads through ocean basins before eventually upwelling in other regions. This circulation pattern depends critically on the formation of cold, dense water in polar regions, particularly around Antarctica and in the North Atlantic, Cambrian oceans. Lacking polar ice and maintaining warm temperatures even at high latitudes could not generate the intense deep water formation that characterizes modern thermohaline circulation. Instead, ocean circulation was driven primarily by wind stress on surface waters, creating wind-driven gyres similar to modern subtropical gyres, but extending across different geographical patterns due to the distinctive continental configuration. The Panthalassa Ocean, dominating the globe like an enlarged Pacific, developed large clockwise and counterclockwise gyres in subtropical latitudes of the northern and southern hemispheres, respectively, driven by trade winds near the equator and westerlies at mid-latitudes. The relatively warm, uniform ocean temperatures created weaker vertical stratification than characterizes modern seas. Modern oceans feature sharp thermoclines, boundaries separating warm surface waters from cold deep waters, that restrict vertical mixing and create distinct layered structures. Cambrian oceans, with more modest temperature differences between surface and deep waters, exhibited weaker thermal stratification, potentially allowing greater vertical mixing. However, the warm climate and elevated biological productivity could generate chemical stratification, with oxygen-depleted deep waters isolated from oxygenated surface layers despite relatively uniform temperatures. Upwelling regions, areas where deep waters rise to the surface, bringing nutrients that fuel biological productivity, operated during the Cambrian just as they do today, driven by wind patterns and the Coriolis effect deflecting surface currents. Along the western margins of ocean basins, where trade winds pushed surface waters offshore, deeper waters upwelled to replace them, creating nutrient-rich zones supporting abundant marine life. These upwelling systems probably played crucial roles in maintaining biological productivity, despite the overall warm conditions and potential oxygen stress in deeper waters. Storm systems in the Cambrian atmosphere likely differed in intensity and frequency from modern patterns due to the altered temperature structure and moisture distribution. Tropical cyclones, hurricanes and typhoons form when warm ocean waters exceed approximately 26.5 degrees Celsius, providing the thermal energy to power these massive rotating storms. With Cambrian sea surface temperatures reaching 28 to 38 degrees Celsius in tropical regions, conditions favored tropical cyclone formation across vast areas. However, the weaker temperature gradients and altered atmospheric circulation patterns may have affected storm tracks and intensities in ways climate models struggle to resolve precisely. The bare, vegetation-free continents profoundly influenced regional climate patterns through their effects on surface albedo, the fraction of incoming sunlight reflected back to space. Modern vegetated landscapes absorb 80 to 90% of incoming solar radiation, with only 10 to 20% reflected. Bare rock and desert surfaces, by contrast, reflect 20 to 40% of sunlight depending on their color and composition. This higher albedo of Cambrian continents meant they absorbed less solar energy than modern vegetated landscapes, potentially creating cooler continental temperatures than would otherwise occur under such high atmospheric carbon dioxide levels. Dust storms represented more significant meteorological phenomena during the Cambrian than they do in the modern vegetated world. Without plant cover to stabilize soils and protect surfaces from wind erosion, strong winds could lift vast quantities of dust from exposed surfaces and transport it across continents and oceans. These dust plumes, visible from space if satellites had existed to observe them, would have appeared as brown streamers extending thousands of kilometers downwind from source regions. The dust itself, rich in iron and other minerals, fertilized ocean waters when it settled on marine surfaces, potentially influencing biological productivity in regions far from continental margins. The carbon cycle operated differently in this vegetation-free world. with important implications for long-term climate regulation. In the modern Earth system, terrestrial plants play crucial roles in carbon cycling through photosynthesis, which removes carbon dioxide from the atmosphere and incorporates it into organic matter. When plant material becomes buried and preserved in sediments, this carbon remains sequestered for millions of years, removing it from the active carbon cycle and gradually drawing down atmospheric carbon dioxide concentrations. During the Cambrian, marine photosynthesis by cyanobacteria and algae provided the primary mechanism for removing carbon dioxide from the atmosphere, but the efficiency of this process remained limited compared to the later vegetated world. Continental weathering of silicate rocks represented another crucial component of the carbon cycle, operating through chemical reactions where carbon dioxide dissolved in rainwater forms weak carbonic acid that breaks down minerals in exposed rocks. The dissolved products, calcium, magnesium, bicarbonate ions, wash into oceans where they precipitate as carbonate rocks, effectively transferring carbon from the atmosphere to long-term geological storage. This weathering process operates as a planetary thermostat, accelerating during warm periods when enhanced rainfall and higher temperatures speed chemical reactions, drawing down carbon dioxide and cooling the climate. During cool periods, reduced weathering allows volcanic carbon dioxide emissions to accumulate, warming the climate back toward equilibrium. In the Cambrian greenhouse world, this weathering thermostat operated at high intensity due to the warm, humid conditions and the extensive exposed rock surfaces available for weathering. The Transgondwanan supermountain and other orogenic belts shed enormous quantities of dissolved minerals into adjacent seas, driving massive carbonate deposition on continental shelves. Yet despite this enhanced weathering, atmospheric carbon dioxide remained elevated, indicating that volcanic outgassing and other carbon sources exceeded the removal rates through weathering and carbonate precipitation. At 500 million years ago, Earth's climate system operated in a warm, relatively stable state that would persist throughout much of the subsequent Ordovician period. This greenhouse world, so different from the glacially punctuated climate characterizing much of the Phanerozoic eon, created the environmental conditions supporting the diverse marine ecosystems preserved in Cambrian fossil deposits. The warm temperatures, high sea levels, and extensive shallow seas provided ideal habitats for the explosive diversification of animal life, while the harsh, vegetation-free continents remained largely empty, awaiting the evolutionary innovations that would eventually enable terrestrial colonization and transform Earth's surface as profoundly as the Cambrian Explosion had transformed its oceans. Among the most remarkable biological innovations of the early Cambrian was the construction of reefs, massive submarine structures, built by living organisms that rose meters above surrounding seafloors, creating complex three-dimensional habitats supporting diverse ecological communities. These were Earth's first true metazoan reefs, constructed not by algae or microbial mats, as earlier Precambrian structures had been, but by animals actively secreting calcium carbonate skeletons and assembling into frameworks resistant to wave action. The organisms responsible for this revolutionary development were archaeocyaths, peculiar sessile filter feeders whose very name, meaning ancient cups, describes their characteristic morphology. Archaeocyaths appeared suddenly in the fossil record at the beginning of the Timotean Age, approximately 525 million years ago, with their center of origin located in what is now East Siberia. From this initial appearance, they spread rapidly across the Cambrian world, appearing in other regions during the subsequent Attabanian Age and quickly diversifying into over 100 families. Within just a few million years of their origin, archaeocyath reefs had established themselves along continental margins worldwide, from present-day Australia, occupying much the same region now hosting the Great Barrier Reef, to Antarctica, Spain, Sardinia, Siberia, Newfoundland, Quebec, Labrador, New York, and California. The basic archaeocyath body plan consisted of a conical or vase-shaped calcareous skeleton with distinctive cup-within-cup architecture. An inner wall and an outer wall, both porous and perforated by numerous openings, enclosed a space called the intervallum, the zone between the walls where internal structures including vertical septa and horizontal tabulae subdivided the space into chambers. The entire structure sat upon the seafloor, typically attached directly to hard substrates, with the large central cavity open to the water above. Sizes varied considerably among species, ranging from millimeter-scale forms barely visible to the naked eye up to individuals reaching 300 millimeters in length. Some archaeocyaths lived as solitary organisms, single cups anchored independently to substrates, while others formed colonies where multiple individuals grew in close association, their skeletons merging into complex aggregates. The colonial forms proved particularly important for reef construction, creating frameworks where successive generations built upon the skeletons of their predecessors, gradually accumulating into substantial structures rising meters above surrounding sea floors. The question of how archaeocyaths are fed has generated considerable scientific debate spanning decades. Their porous skeletons suggested a filter-feeding lifestyle analogous to modern sponges, with water flowing through the numerous openings in the outer wall, passing through the intervallum where food particles would be extracted, and exiting through the central cavity. However, whether this water movement occurred passively, driven purely by ambient currents flowing across the organism, or actively through metabolic pumping similar to modern sponges remained contentious. Early experimental work using flume tanks and physical models suggested archaeocyaths functioned as passive suspension feeders, relying entirely on environmental currents to drive water circulation. However, critics pointed out that these experiments used models larger than natural specimens and with inaccurate pore morphologies, factors that directly affect fluid behavior and particle transport. Recent computational fluid dynamics simulations using morphologically accurate digital reconstructions have challenged the passive feeding hypothesis. These CFD analyses demonstrated that under plausible current velocities, very little fluid circulation occurred through archaeocyath skeletons, suggesting obligate passive suspension feeding was unlikely. Comparing simulation results with exhalant water velocities measured in living sponges led researchers to infer that archaeocyaths employed active suspension feeding, metabolically pumping water through their skeletal structures just as modern sponges do, using specialized flagellated cells called choanocytes. This interpretation carries profound implications for understanding Cambrian reef ecology. Active feeding would have freed archaeocyaths from dependence on high-energy environments, where strong currents naturally drive water movement, enabling them to colonize a broader range of settings, including deeper, more sheltered locations. The combination of active suspension feeding with robust calcified skeletons enabled archaeocyaths to construct reef ecosystems on scales unprecedented in Earth's history. Earlier Precambrian structures built by microbial mats, stromatolites and thrombolites had created local topographic relief, but these represented accretions of sediment trapped and bound by bacterial films rather than true framework reefs constructed from mineralized skeletons. Archaeocyath reefs, by contrast, possess structural integrity derived from the interlocking skeletons of countless individual organisms, creating porous frameworks that resisted wave action while simultaneously harboring diverse communities of other organisms within their interstices. These early Cambrian reefs range from small patch reefs, meter-scale bioherms dotting the seafloor like isolated islands, to much larger constructions measuring tens of meters in scale that extended along continental shelves for considerable distances. The largest archaeocyath reef complexes rivaled modern coral reefs in their extent and structural complexity, creating biological features visible on a geological scale that fundamentally transformed marine environments wherever they occurred. The ecological significance of these reef structures extended far beyond the archaeocyaths themselves. By constructing three-dimensional frameworks rising above surrounding seafloors, archaeocyaths created entirely new ecological niches that had not existed during the Ediacaran. The spaces within reef frameworks, cavities, channels, and chambers formed between intergrown skeletons provided shelter for mobile animals, attachment surfaces for sessile organisms, and substrate for algae and microbial films. This habitat diversification enabled a proliferation of reef-dwelling specialists including trilobites, brachiopods, echinoderms, mollusks, and various worm groups, all exploiting resources unavailable in adjacent non-reef environments. The presence of archaeocyath reefs altered local hydrodynamics, modifying current patterns and sediment transport in ways that further enhanced habitat complexity. Reefs acted as baffles, dissipating wave energy and creating sheltered zones in their lee where fine sediments could settle and accumulate. The porous nature of archaeocyath frameworks slowed water movement within the reef structure itself, extending the residence time of water parcels and allowing more complete extraction of suspended nutrients and organic particles. This efficient filtering modified local water chemistry, potentially creating microenvironments within reef interstices that differed chemically and physically from surrounding waters. Unlike modern coral reefs, which depend heavily on photosynthetic zooxanthella algae living symbiotically within coral tissues, archaeocyath reefs presumably lacked photosynthetic symbionts and relied entirely on heterotrophic feeding, capturing organic particles and microorganisms from the water column. This fundamental difference meant archaeocyath reefs were not constrained to shallow, well-lit waters within the photic zone, as modern coral reefs are. Instead, archaeocyaths could colonize deeper waters where light levels proved insufficient for photosynthesis, potentially extending their depth range beyond the limits, characterizing modern coral reef growth. This ability to thrive beyond the photic zone may explain the widespread success of archaeocyath reefs during the early Cambrian and their occurrence in depositional settings ranging from shallow subtidal environments to deeper shelf locations. Modern glass sponge reefs, which also rely on heterotrophic feeding without photosynthetic symbionts, provide a possible analogue for understanding archaeocyath reef ecology. These deep-water sponge reefs, found today in British Columbia coastal waters at depths of 150 to 250 meters, demonstrate that framework-building filter feeders can construct substantial reef structures in aphotic environments where coral reefs cannot exist. The taxonomic diversity of archaeocyaths during their early Cambrian heyday reached remarkable levels, with paleontologists recognizing over 100 families distinguished by variations in skeletal architecture, pore arrangement, septal structure, and overall morphology. These morphological differences likely reflected adaptations to different microenvironments within reef habitats, different feeding strategies, or phylogenetic relationships between lineages diversifying rapidly across the early Cambrian radiation. Some forms featured nested bowl-like structures, while others grew as elongated cones. Some possessed simple septa dividing the intervallum, while others developed complex internal partitions creating elaborate chamber systems. The widespread distribution of archaeocyath species across almost the entire Cambrian world, combined with their taxonomic diversity, suggests they possessed planktonic larval stages that enabled long-distance dispersal, like modern sponges, which release tiny larvae that drift with currents before settling and metamorphosing into sessile adults. Archaeocyaths probably broadcast their offspring into the water column where currents transported them across ocean basins. This dispersal capability explains how archaeocyath species achieved nearly global distributions, despite being sessile organisms, incapable of movement as adults, at 500 million years ago, precisely at the midpoint of the Cambrian period. Archaeocyaths had already passed the apex of their success. The group reached maximum diversity during the Attabanian and Batomian ages of the early Cambrian, between approximately 530 and 513 million years ago. Around 516 million years ago, at the beginning of the Toyonian age, archaeocyaths entered sharp decline. Species richness dropped precipitously, with most families disappearing within a few million years. By the Middle Cambrian, archaeocyath diversity had collapsed to a fraction of its former abundance, and almost all species went extinct before the Middle Cambrian ended. The final known species, Antarcticocyathus weberi, disappeared just prior to the end of the Cambrian period, though recent reinterpretation of this fossil as a lithistid sponge rather than a true archaeocyath suggests the group may have actually gone extinct even earlier, during the Middle Cambrian. Regardless of the precise timing, the decline and disappearance of archaeocyaths occurred relatively rapidly, geologically speaking, after their initial appearance and diversification. The causes of archaeocyath decline and eventual extinction remain subjects of debate, though several factors likely contributed. Competition from more modern demosponges, which were diversifying rapidly during the Middle Cambrian, may have displaced archaeocyaths from favorable habitats. The demosponges possessed more flexible body plans, more efficient feeding mechanisms, and possibly superior abilities to resist predation, environmental stress, or disease. As these more advanced sponges radiated into niches previously occupied by archaeocyaths, the ancient cup builders may have found themselves outcompeted and gradually excluded from the reef environments they had dominated. Environmental changes during the Middle and Late Cambrian also potentially contributed to archaeocyath decline. Shifts in ocean chemistry, temperature fluctuations, changes in sea level, or modifications to nutrient availability could have stressed archaeocyath populations already facing biological competition. The Middle Cambrian crisis that affected trilobites and other groups may have similarly impacted archaeocyaths, driving extinctions among forms that could not adapt to changing conditions. Following the extinction of archaeocyaths, reef ecosystems became extremely rare throughout the remainder of the Cambrian and well into the subsequent Ordovician period. This interval, spanning roughly 20 to 30 million years, represents one of the most significant reef gaps in the Phanerozoic fossil record, when carbonate accumulations and framework reef structures essentially disappeared from the geological record. The absence of major reef builders during this interval suggests that archaeocyath extinction left an unfilled ecological niche that persisted until new groups, including tabulate and rugose corals, stromatoporoid sponges, and bryozoans, evolved reef-building capabilities during the Ordovician radiation. The archaeocyath legacy, though brief in geological terms, established crucial precedents for all subsequent reef ecosystems. They demonstrated that metazoan organisms could construct massive carbonate frameworks, creating complex three-dimensional habitats supporting diverse ecological communities. They showed that suspension-feeding filter feeders could achieve sufficient abundance and biomass to dominate shallow marine environments, and they revealed the profound importance of biological engineering organisms, modifying their physical environment in ways that create new ecological opportunities in shaping the trajectory of evolutionary diversification. At 500 million years ago, in the Middle Cambrian, the Archaeocyath dynasty approached its end. Their reefs, which had dominated tropical and subtropical shelves for 25 million years, were crumbling into relic structures where erosion gradually dismantled frameworks no longer maintained by living organisms. Yet the ecosystems they had nurtured and the evolutionary innovations they had fostered in reef-dwelling communities would persist and flourish long after the last archaeocyath vanished from Earth's oceans. Among the most consequential innovations of the Cambrian explosion was the widespread appearance of mineralized shells, hard, protective coverings that fundamentally altered marine ecology and left an abundant fossil record preserving the diversification of animal life. Two major groups of shelled organisms dominated Cambrian seafloors: brachiopods, which would become the most abundant marine invertebrates throughout much of the Paleozoic era, and mollusks, whose descendants would eventually inherit the oceans and achieve even greater diversity than brachiopods ever attained. At 500 million years ago, both groups had already established themselves as significant components of marine ecosystems, though their evolutionary trajectories and ultimate fates would diverge dramatically. Brachiopods first appeared in rocks of earliest Cambrian age, approximately 541 to 535 million years ago, arriving on the evolutionary stage fully formed with well-developed shells, articulation mechanisms, and complex feeding structures. This sudden appearance in an advanced state of development indicates a long prior evolution from shellless ancestors, a history apparently lost or unrecorded in Precambrian rocks, where preservation conditions rarely captured soft-bodied organisms. The earliest brachiopods belonged to the inarticulata forms, lacking the sophisticated hinge mechanisms that would characterize later articulate brachiopods, and these simple forms quickly became the most abundant brachiopods of the early Cambrian period. The basic brachiopod body plan consists of two shells or valves that enclose the soft body, superficially resembling bivalve mollusks in overall appearance, but differing fundamentally in anatomy and orientation. In brachiopods, the two valves differ in size and shape, with dorsal and ventral valves positioned perpendicular to the animal's body axis, while in bivalves, the two valves are typically similar and positioned on left and right sides. This distinction reflects the separate evolutionary origins of these groups. Brachiopods and mollusks evolved shells independently, arriving at superficially similar solutions to the challenge of protection through entirely different developmental and genetic pathways. Within the brachiopod valves sits the lophophore, the defining feature of the phylum Brachiopoda, and related groups including bryozoans. This complex feeding structure consists of a horseshoe-shaped or coiled tentacular crown bearing thousands of ciliated tentacles that generate water currents, filter suspended particles from incoming water, and transport captured food toward the mouth. The sophistication of brachiopod lophophores varies enormously across different groups, from simple loops in primitive forms to elaborate spiral structures in advanced species. This feeding apparatus enables brachiopods to function as efficient suspension feeders, capturing phytoplankton, bacteria, and organic detritus from the water column, while remaining sessile permanently, attached to substrates. Early Cambrian brachiopods secreted shells composed primarily of calcium phosphate rather than the calcium carbonate that characterizes most later forms. These phosphatic shells, particularly common among linguliform brachiopods, exhibit remarkable preservation in the fossil record due to phosphate minerals' resistance to dissolution. Recent research examining exquisitely preserved specimens from the Cambrian Series 2 Shuijing Tuo Formation of South China reveals extraordinary detail about these early shell structures, including hierarchical architectures built from stacked cylindrical columns arranged in sandwich-like units. The biomineralization process creating these columnar shell architectures represents a highly biologically controlled and organic matrix-mediated innovation that played significant roles in linguliform evolution. The calcium phosphate-based shells, composed of stacked sandwich columnar units, required sophisticated cellular machinery to secrete and organize mineral crystals within organic frameworks. The epithelial cells responsible for shell secretion left distinctive molds preserved in some fossils, providing rare glimpses into the cellular-level processes. Underlying skeleton construction. During the Cambrian Explosion, the diversity of columnar shell structures among early phosphatic-shelled brachiopods demonstrates rapid morphological evolution and ecological specialization. Species like Latusobolus, Xiaoyangbiensis, and Eobolus acuteolus from the early Cambrian exhibit relatively simple stacked sandwich columnar architectures with small columns and thin shells, limiting both valve thickness and overall body size to millimeter scales. These tiny brachiopods occupied specific ecological niches in early Cambrian seafloor communities, possibly exploiting secondary tiering positions, elevated above the sediment-water interface on organic stalks, where they filtered food from faster-moving currents. In contrast, acrotretide brachiopods fully utilize columnar architecture across their entire clade, developing derived camrate fabrics, more complex shell structures incorporating greater amounts of mineralized material arranged in elaborate patterns. The columns in acrotritides increased to approximately 10 times the height of those in primitive lingulides, with corresponding increases in the number of stacked sandwich units. Despite these larger columns, acrotritide bodies remained restricted to millimeter dimensions, suggesting trade-offs between the metabolic costs of phosphate, biomineralization, and the mechanical advantages of robust skeletal protection. The continuous transformation of anatomical features revealed in the fossil record demonstrates evolutionary connections between Eobolidae, Lingulellotretida, and Acrotretida, three major groups of early phosphatic-shelled brachiopods. This gradual transition from simple to complex columnar architectures sheds light on adaptive innovations that enabled these tiny organisms to flourish during the Cambrian radiation and persist through the subsequent Great Ordovician biodiversification event, thriving in marine benthic communities for more than 100 million years. Articulate brachiopods, those with sophisticated hinge mechanisms enabling precise valve articulation, appeared alongside inarticulate forms at the beginning of the Cambrian, though their initial diversity remained modest compared to inarticulate groups. These early articulates represented specialized forms that would eventually give rise to the spectacular diversity characterizing brachiopods throughout the remainder of the Paleozoic era. The articulate body plan proved remarkably successful, enabling brachiopods to adapt to nearly every marine environment from intertidal zones to deep basins. By the Middle Cambrian, our 500 million year focal point, brachiopods had already diversified into numerous families occupying diverse ecological niches. Inarticulate forms remained abundant, but had begun their long-term decline that would continue throughout subsequent periods. Articulate brachiopods, though still relatively uncommon in Middle Cambrian faunas, were poised for the explosive radiation that would characterize the Ordovician period, when they would achieve dominance in shallow marine habitats worldwide. Mollusks followed a different evolutionary trajectory during the Cambrian, though they too appeared early in the period with well-developed shells and complex anatomies. The major mollusk classes, gastropods, snails, cephalopods, squid relatives, and bivalves, clams and relatives, all have fossil representatives in Cambrian rocks, demonstrating that the fundamental body plans characterizing these groups had already diverged by the early Cambrian. Debate continues about whether some Ediacaran fossils represent early mollusks or mollusk ancestors, but unambiguous mollusks certainly existed by 530 million years ago. Early Cambrian gastropods included primitive forms crawling across seafloors, grazing on algae and bacterial films, and exploiting food resources unavailable to sessile filter feeders like brachiopods. Their mobile lifestyle, combined with the protective shell that they could withdraw into when threatened, provided adaptive advantages in increasingly predator-filled Cambrian seas. The torsion characterizing gastropod anatomy, a developmental process where the visceral mass rotates relative to the head and foot, had already evolved by the early Cambrian, producing the characteristic asymmetric body plan that distinguishes gastropods from other mollusks. Cephalopods, the most sophisticated mollusks in terms of nervous system complexity and behavioral capabilities, appeared during the late Cambrian, though their origins likely extend back to the Middle Cambrian or earlier. The earliest cephalopods possessed simple conical shells divided into chambers by transverse septa, with the animal occupying the largest, most recent chamber, while gas-filled older chambers provided buoyancy. This chambered shell design, perfected over subsequent millions of years, enabled cephalopods to achieve neutral buoyancy and exploit pelagic niches unavailable to benthic gastropods and bivalves. Bivalves, the clams, oysters, mussels, and scallops that would eventually dominate many marine environments, appeared during the Cambrian as relatively minor components of seafloor communities. Early bivalves possessed simple shells consisting of two similar valves connected by a flexible ligament and held together by adductor muscles. Unlike brachiopods, which actively pump water through their shells using ciliary action on their lophophores, Bivalves are passive filter feeders that extend siphons into the water column and rely on ciliary currents along their gill surfaces to capture suspended particles. The ecological roles of Cambrian bivalves remained limited compared to their later descendants. Most lived as shallow burrowers in soft sediments, filtering food from water pumped through their buried bodies, or as epifaunal forms attached to hard substrates. The deep burrowing capabilities, boring lifestyles, swimming behaviors, and reef-building habits that characterize many modern bivalves had not yet evolved during the Cambrian. Brachiopods dominated hard substrate environments where sessile filter feeders thrived and would continue their dominance for another 250 million years. The Middle Cambrian seas at 500 million years ago witnessed both brachiopods and mollusks occupying distinct but overlapping ecological zones. Brachiopods achieved greater abundance and diversity, particularly in shallow marine environments where their sessile filter-feeding lifestyle proved highly successful. Phosphatic-shelled lingulliforms occupied soft substrates, anchoring themselves with organic pedicles, extending from their ventral valves into sediments below. Articulate brachiopods colonized hard surfaces, cementing their ventral valves directly to rock substrates or attaching via mineralized pedicles. Mollusks pursued more diverse ecological strategies. Gastropods crawled across surfaces, exploiting mobility to access food resources and avoid predators. Early cephalopods, though still rare in Middle Cambrian faunas, represented the first active predators among mollusks, using tentacles to capture prey and beaks to process food. Bivalves in faunal lifestyles, buried within sediments with only feeding siphons extending above the seafloor, enabled them to avoid many surface predators while accessing nutrients suspended in bottom waters. The contrasting fates awaiting these two groups, brachiopods and mollusks, could not be predicted from their Middle Cambrian distributions. Brachiopods would dominate Paleozoic seas, achieving spectacular diversity during the Ordovician and Silurian periods when they became adapted to virtually every marine environment and reached population densities, forming whole banks of shells in shallow waters. Their shells would constitute major components of limestone strata and reef deposits throughout the Paleozoic. Yet the end Permian mass extinction, 252 million years ago, would devastate brachiopods, eliminating most lineages and dramatically reducing their ecological importance. From their pre-extinction dominance, brachiopods would decline throughout the Mesozoic and Cenozoic eras, increasingly replaced by bivalve mollusks in many former brachiopod habitats. The causes of this replacement remain debated. Competition from filter-feeding bivalves, increased predation pressure, disturbance of sediments by burrowing organisms, or simply chance demise following the severe Permian extinction from which brachiopods never fully recovered. Mollusks, by contrast, would continue their steady rise in diversity from the mid-Paleozoic onward, weathering mass extinctions more successfully than brachiopods, and eventually achieving the extraordinary success characterizing them today. Modern oceans host approximately 100,000 living mollusk species occupying virtually every marine habitat from intertidal zones to abyssal trenches, while brachiopods persist only in limited numbers. Perhaps 400 living species inhabiting largely marginal environments. At 500 million years ago, these future trajectories remained invisible. The Middle Cambrian oceans supported diverse communities where brachiopods and mollusks coexisted successfully, each group exploiting different resources and occupying distinct ecological niches. Their mineralized shells, constructed through sophisticated biomineralization processes from calcium phosphate or calcium carbonate, provided protection, enabling survival in increasingly predator-dominated ecosystems, while simultaneously creating an abundant fossil record, preserving the details of their diversification. These shelled animals, along with arthropods, echinoderms, and other mineralized groups, established the marine ecosystems that would characterize Earth's oceans throughout the remainder of the Phanerozoic eon.